What if the very foundation of reality, the seemingly smooth, continuous stage upon which all events unfold, isn't solid at all, but is instead a chaotic, frothing ocean of pure energy and possibility? This isn't science fiction, it's a leading edge of modern physics that challenges everything we think we know about the cosmos. We are about to dive deep past planets and stars, beyond galaxies and black holes, to the most fundamental level of existence itself, a seething, turbulent realm known as quantum foam. At this unimaginably tiny scale, the concepts of here and now break down completely. Space and time themselves lose their steady, reliable nature, bubbling and churning with virtual particles that wink in and out of existence in a frenzied dance governed by the bizarre laws of quantum mechanics. This is the universe's ultimate substrate, the hidden engine of reality that operates far beneath our everyday perception. For centuries, we imagined the vacuum of space as a perfect, empty void, a silent and sterile nothingness. But the quantum foam tells a radically different story. It paints a picture of a vacuum that is alive, a vibrant, effervescent sea where so-called empty space is the most active place of all. In every single cubic centimeter of what appears to be nothing, countless virtual particle pairs are constantly borrowing energy from the universe, appearing for the briefest of moments before annihilating each other and vanishing back into the energetic haze. This relentless creation and destruction is not a calm process. It's a storm of unimaginable ferocity, happening at scales a billion trillion times smaller than an atomic nucleus. Contemplating this reality can feel dizzying, as if the solid ground beneath our feet has transformed into a shimmering, unstable mist. And the most incredible part is that we are not merely passive observers of this cosmic turbulence. We are woven from it, products of this same chaotic genesis. The journey we are beginning today is an exploration of the greatest minds and the most profound ideas that attempt to make sense of this bewildering foundation. We will navigate 30 incredible theories, each one a daring attempt to map the uncharted territory of the quantum foam. From proposals that our universe is a holographic projection to ideas that suggest a foam-like structure could be the key to unifying all the forces of nature, we will uncover the boldest and most mind-expanding concepts in theoretical physics. This voyage will challenge your intuition, inspire a sense of profound wonder, and reveal why understanding this frothy, fundamental layer of reality might just hold the answers to the universe's oldest and deepest mysteries. So let's begin. Our first stop on this journey takes us back to the visionary mind of physicist John Archibald Wheeler. In the 1950s, Wheeler was grappling with the strange implications of quantum mechanics for the fabric of spacetime itself. He proposed that if we could peer down to the absolute smallest possible scale, a distance known as the Planck length, the smooth, predictable geometry of Einstein's universe would vanish. In its place, we would find a state of ultimate chaos and turbulence. Wheeler famously named this concept quantum foam, but he also gave it another, more descriptive title, geometrodynamics. This name captures the essence of the idea that the very geometry of space is not static but wildly dynamic. Instead of a flat, calm plane, the foundation of reality resembles a churning ocean during a storm, with waves, bubbles, and whirlpools of pure geometry constantly forming and dissolving. At this unimaginably tiny scale, the concepts of here and there or before and after lose all meaning. The orderly grid of spacetime is shattered into a frothing, probabilistic frenzy. What does this foam actually consist of? According to Wheeler's theory, the turbulent energy at this level manifests as a seething soup of temporary structures. Microscopic wormholes, acting like tiny shortcuts through space, would blink into existence for a fleeting moment before collapsing. Simultaneously, an incalculable number of virtual black holes, each far smaller than a single atom, would pop in and out of being, their intense gravitational fields warping the geometry around them in a frantic dance. This isn't a calm, empty vacuum. It's the most active and violent place imaginable, a cauldron of creation and annihilation where the universe is constantly remolding its own fundamental structure. The energy for this relentless activity is borrowed from the universe, in perfect accordance with Heisenberg's uncertainty principle, which allows for such brief, violent fluctuations as long as they don't last long enough to violate the conservation of energy. To grasp how radical this idea is, picture the screen you're watching this on. From a distance, it looks like a smooth, continuous image, but if you move closer, you see the individual pixels. Move closer still, and you might see the subpixels and the complex electronic dance that creates each point of light. Wheeler's quantum foam suggests that spacetime itself has a fundamental pixelation, but these pixels aren't neat little squares. They are a chaotic, ever-changing foam of topological fluctuations. This isn't just empty space, this is space. The foam isn't in spacetime, the foam is spacetime at its most fundamental level. This foundational chaos has profound implications, suggesting that the perfect vacuum of classical physics is a myth. Instead, every single point in the universe, from the void between galaxies to the space inside the atoms of your own body, is home to this unimaginably intense microscopic storm. This relentless churning of the quantum foam might seem like an untestable, abstract concept, but its effects ripple upward into our macroscopic world in a way we can actually measure. To understand how, we need to look at the primary actors in this microscopic drama of virtual particle pairs. According to quantum field theory, the empty vacuum is not empty at all. It is a seething ocean of potential where pairs of particles and their corresponding antiparticles spontaneously burst into existence. These aren't permanent particles you could trap in a box. They are fleeting fluctuations, borrowing energy from the universe for a time so brief it defies comprehension, mandated by Werner Heisenberg's uncertainty principle. A particle and its antiparticle partner appear together, live for a mere whisper of a moment, and then rush back together, annihilating each other and returning the borrowed energy to the vacuum from which they came. This isn't a rare event. It's happening everywhere, all the time, in every single point of space, creating a background hum of existence that forms the very baseline of reality. Now, how do we move from this invisible, frenetic dance to something we can actually observe? The bridge is a remarkable phenomenon known as the Casimir effect, named after the Dutch physicist Hendrik Casimir, who predicted it in 1948. Imagine taking two perfectly smooth, uncharged metal plates and placing them incredibly close together in a perfect vacuum, so close that the gap between them is smaller than the width of a human hair. In the vast, open space outside the plates, virtual particles of all possible wavelengths or energies can pop into existence. However, in the narrow gap between the plates, only certain wavelengths can fit specifically, those wavelengths that are whole fractions of the gap distance. It's like the difference between the open ocean, where waves of any size can form, and a very narrow canal, which only permits waves of a specific size to exist. This restriction has a profound consequence. The constant pressure from the virtual particles outside the plates becomes greater than the pressure from the more limited set of particles able to form between them. The result is a net inward force that pushes the two plates together. This isn't some theoretical fantasy. This force has been measured repeatedly in laboratory experiments with exquisite precision. The Casimir effect is a direct, tangible footprint of the quantum foam. It provides stunning experimental evidence that what we call a vacuum is truly alive with transient energy, and that by manipulating space itself, by restricting which virtual particles can form where, we can elicit a real, physical force out of nothing but the intrinsic activity of the void. It's as if by squeezing space, we are wringing out a latent energy we didn't know was there, revealing the profound truth that nothingness, when examined closely, is the most something of all. But what if Wheeler's stormy ocean of foam is actually a liquid? This brings us to a theory that completely reimagines the fundamental nature of reality, suggesting that spacetime is not a static stage or a chaotic foam, but a fluid. And not just any fluid, but a superfluid, a quantum liquid that flows without any viscosity or friction whatsoever. In this mind-bending picture, the entire universe is submerged in an exotic, continuous medium. The quantum foam we've been discussing, with all its frenetic bubbling and virtual particles, could then be understood not as a fundamental chaos, but as the natural texture of this superfluid. Just as heating water causes it to bubble and churn, the intrinsic energy of the vacuum could be causing spacetime itself to exhibit a foamy structure. It's a shift from thinking of spacetime as a thing to thinking of it as a substance with its own unique properties and behaviors. The concept of a superfluid isn't pure speculation. We create them in laboratories here on Earth. When certain isotopes of helium are cooled to temperatures near absolute zero, they undergo a dramatic transformation, becoming superfluids. These liquids can do things that seem to defy common sense. They flow up and over the sides of their containers in a thin film. They can never be stirred to form vortices in the way normal liquids can, and they can seemingly forever without losing any energy. If spacetime shares these properties, it would mean that the fabric of the cosmos has zero resistance to motion or change at a fundamental level. This could provide an elegant explanation for why the universe seems so smooth and uniform on large scales. A superfluid spacetime would naturally settle into a state of equilibrium, effortlessly smoothing out any wrinkles or irregularities over vast cosmic distances. So where does the foam come in? Even in a perfect superfluid, imperfections and excitations can arise. Think of a perfectly still, crystal-clear river. If you introduce a tiny obstacle or enough energy, you can create whirlpools and eddies. In the superfluid spacetime model, the violent fluctuations of the quantum vacuum, the popping in and out of virtual particles and energy, could be analogous to these tiny vortices and excitations. The foam, then, is the microscopic turbulence on the surface of this ultimate fluid. Each tiny wormhole or quantum fluctuation could be a momentary whirlpool in the superfluid medium, a place where the perfect, frictionless flow is briefly disrupted before calming back down. This provides a potential physical mechanism for the foam, framing it not as random chaos, but as a natural consequence of a fluid like spacetime under constant excitation. Perhaps the most compelling aspect of this theory is its potential to solve one of astronomy's greatest mysteries, dark matter. We observe that galaxies rotate much faster than they should based on the amount of visible matter they contain. Something invisible must be providing the extra gravitational pull to hold these galaxies together. The superfluid spacetime theory offers a radical alternative to the idea of an unknown, invisible particle. Instead, what if the missing gravity isn't from a particle at all, but from the fluid nature of spacetime itself? In this model, as galaxies rotate, they would gently drag the superfluid spacetime around with them. This dragging effect could create a subtle gradient in the fluid's density or pressure, and this gradient itself could generate an additional gravitational field, exactly the kind of effect we attribute to dark matter. The ghostly halo of dark matter surrounding a galaxy might not be a cloud of particles, but the faint gravitational imprint of the galaxy's interaction with the superfluidic medium in which it is immersed. But if the idea of a superfluid spacetime stretches your imagination, prepare for a concept that takes granularity to its ultimate conclusion. This is the world of loop quantum gravity, or LQG, a theory that proposes something truly radical. That space itself is not smooth and continuous, but is actually composed of tiny, indivisible building blocks. Think of it this way: for centuries we thought matter was continuous until we discovered it was made of atoms. Then we discovered that energy also comes in discrete packets called quanta. LQG completes this revolution by declaring that the fabric of space and time is also pixelated. It proposes that there is a smallest possible unit of volume, a true atom of space beyond which you cannot divide further. In this theory, the quantum foam isn't just a chaotic storm. It's the dynamic, ever-changing structure of this fundamental granular reality. So, what is the actual structure of these atoms of space? Loop quantum gravity paints a beautiful and intricate picture. It suggests that space is woven together from tiny, one-dimensional loops of gravitational field. Imagine an incredibly fine cosmic mesh, but instead of being made of rigid threads, it's made of these vibrant, vibrating loops. These fundamental loops don't exist in space. They themselves are the fabric of space. They connect with one another, intersecting and linking to form a vast, tangled network known as a spin network. Each individual intersection or node in this network represents a tiny, discrete volume of space, while the links between them define how these volumes are adjacent to one another. The entire three-dimensional structure of the universe around you, from the space inside a coffee cup to the vast voids between galactic clusters, emerges from the specific way this immense cosmic tapestry is woven together. This is where the quantum foam re-enters the picture in a spectacular way. The spin network isn't a static, frozen structure. It's a dynamic quantum entity that evolves over time. The entire network pulses and changes, with loops fluctuating and links reconfigured in a process governed by the laws of quantum mechanics. This evolving structure is called a spin foam. Think of a spin network as a single, still frame in a movie of the universe. The spin foam is the entire movie reel, capturing the dynamic history of how space itself changes from one moment to the next. Each little bubble or cell in this foam represents a quantum event, a fundamental change in the geometry of space, like a tiny volume of space transitioning to a new configuration. The frenetic bubbling and churning that Wheeler envisioned in his original quantum foam concept finds a precise mathematical description here. It is the dynamic dance of the spin foam, the constant probabilistic rewriting of the universe's spatial relationships at the Planck scale. The implications of this are staggering. Because space is quantized, there is no such thing as a true mathematical point or an infinitely small distance. There is only a finite number of these atoms of space in any given volume. This solves a major problem that plagues other theories of gravity, the problem of singularities. In Einstein's general relativity, when matter collapses under its own gravity to form a black hole, or when we rewind the cosmos to the Big Bang, the math predicts points of infinite density and curvature, places where the laws of physics simply break down. But in loop quantum gravity, you cannot compress matter and energy into an infinitely small point because space itself has a smallest possible volume. Matter can only be compressed so far until it fills up these fundamental cells of space. This leads to a breathtaking prediction. The Big Bang might not have been a singularity at all, but a big bounce, a moment of extreme but finite density where a previous universe contracted before rebounding into our own expanding cosmos. The quantum foam, in its most advanced theoretical form, might not only explain the texture of space, but also the ultimate origin of our universe. Now, prepare to have your entire perception of dimensionality turned inside out, because our next theory is perhaps the most radical of them all. It suggests that everything we consider to be real, the three-dimensional fullness of the cosmos, the stars, the planets, and even you and I, might be nothing more than a magnificent illusion. This is the holographic principle, a concept so profound that it redefines the nature of reality itself, proposing that our universe is a vast and incredibly complex hologram. To grasp this, think of a standard security hologram on a credit card. That shimmering, three-dimensional image isn't truly deep. It's encoded on a flat, two-dimensional plastic surface. The holographic principle applies this same logic to the entire cosmos, suggesting that all the information that makes up our three-dimensional reality, including the frantic churning of the quantum foam, is actually stored on a distant two-dimensional boundary that surrounds us. So, where is this cosmic projector screen? In the most common formulation of the theory, this two-dimensional surface is the universe's event horizon, the ultimate boundary of our observable cosmos. All the information about every galaxy, every particle, and every event happening within our three-dimensional volume is somehow painted onto this vast spherical shell. What we experience as depth, texture, and the very passage of time is just a projection from that surface, a kind of cosmic decoding of that information into the rich tapestry of reality we perceive. This isn't just a philosophical idea. It emerged from the study of black holes in the 1990s. Physicists, including Leonard Susskind and Gerard T. Hooft, realized that the maximum amount of information a region of space can contain isn't proportional to its volume, as you might expect, but to the area of its boundary. This was a stunning revelation. It implies that a three-dimensional space can be completely described by a theory that operates in one less dimension on its surface. The world we see is a translation, a rendering of data stored on the edge of the universe. This leads to a mind-bending implication for the quantum foam. If our reality is a holographic projection, then the wild, turbulent chaos of the foam, the wormholes, virtual black holes, and probabilistic frenzy at the Planck scale might not be the fundamental bedrock of reality after all. Instead, it could be a secondary effect, a kind of visual static or computational artifact that emerges from the process of translating the perfectly orderly two-dimensional data into a three-dimensional experience. The foam's complexity is an illusion, a consequence of the projection mechanism itself. It would be like looking closely at a high-definition television screen. From a distance, the image appears smooth and continuous, but up close, you see the individual pixels and the underlying digital noise that creates the picture. The quantum foam could be the ultimate pixelation of our cosmic movie, the graininess that appears when we examine the projection of reality at its highest possible resolution. How could this possibly work? The mathematics points to a concept known as entanglement. The bits of information on the two-dimensional boundary are thought to be wildly entangled with one another in an incredibly complex web of quantum connections. It is this dense network of correlations that, when projected, generates the geometry and physics of our three-dimensional world. The apparent randomness and uncertainty of the quantum foam could simply be the three-dimensional manifestation of the incredibly complex, but ultimately orderly, information processing happening on the boundary. This provides a potential solution to one of the biggest puzzles in theoretical physics, the problem of unifying gravity with quantum mechanics. In the holographic picture, gravity in our three-dimensional world isn't a fundamental force in the same way as the others. It emerges along with the very dimension of space from the quantum interactions on the lower dimensional surface. The foam-like structure of spacetime is not the cause but the effect. This radically alters our search for a final theory. Instead of seeking a theory of quantum gravity that operates within our three-dimensional space, the holographic principle suggests the true, simpler theory exists on the two-dimensional boundary. The universe's deepest secrets aren't hidden in the chaotic heart of the quantum foam, but are written in a cleaner, more fundamental language on the cosmic horizon. Our perceived reality, in all its vast, foamy complexity, is a magnificent shadow, a rich and detailed illusion cast by a deeper, simpler truth encoded at the very edge of everything we can ever know. While the holographic principle suggests our reality might be a projection from a distant boundary, another powerful theory takes a more hands-on, engineering approach to the fabric of the cosmos. This idea, known as causal dynamical triangulations, asks a beautifully simple question. What if we could build space-time itself, piece by microscopic piece, like assembling a universe from cosmic Lego bricks? This approach sidesteps the complex equations of other theories and instead uses the raw power of computer simulations to watch spacetime emerge from scratch. The fundamental building blocks aren't mysterious loops or fields, but the simplest geometric shapes possible: tiny, perfect triangles and their higher dimensional cousins called simplices. In 4 dimensions, these are 4 simplices, the elemental chunks of spacetime, each one representing the smallest possible event, a union of a tiny bit of space with a tiny bit of time. The theory then provides a single, elegant rule for how these pieces are allowed to snap together. They must connect in a way that rigorously preserves causality, meaning that cause must always come before effect in the assembly. You can't have a building block that represents an effect connecting to one that is its cause. The fundamental arrow of time is woven directly into the latticework of reality from the very first moment. So, what happens when you tell a supercomputer to take trillions upon trillions of these tiny causal simplices and randomly assemble them following these simple rules? The answer is nothing short of magical. At the very smallest scales, the simulation reveals a wildly fluctuating, chaotic environment. If you could shrink down to the Planck length, you would find a bizarre, fractal-like geometry. It's a foamy, crumpled mess of dimensions where the very concept of smooth has no meaning. This is the quantum foam in its purest computational form, a spacetime that is fundamentally discontinuous and wildly fluctuating. The simulations show that at these ultra-microscopic scales, the dimensionality of space doesn't settle on a neat value of 3. Instead, it fluctuates, with some regions behaving as if they have fewer dimensions, creating a complex, frothy texture that is the direct result of the random, yet causal, gluing of these fundamental pieces. But here is the true wonder of causal dynamical triangulations, the result that stunned its creators. As you zoom out from this microscopic frenzy, a miracle of emergence occurs. All those chaotic, random connections and fractal fluctuations begin to average out. Just as the frantic jostling of countless water molecules averages out to produce the smooth, predictable flow of a river, the unimaginably complex interactions of the simplices cancel each other out and give rise to a large-scale structure that is remarkably smooth, continuous, and 4-dimensional. From the incomprehensible chaos of the foam, our familiar classical universe spontaneously crystallizes. This is a profound revelation. The smooth spacetime of Einstein's general relativity isn't fundamental. It is a collective phenomenon, an average description that works perfectly well for large scales and long durations, but which completely masks the violent, discrete, and foamy truth of the microscopic world. The universe we experience is a statistical illusion, a stable phase that emerges from the ceaseless, causal interactions of its smallest parts. This success provides a powerful new perspective on the quantum foam. It's not merely a sea of random fluctuations, but a dynamic, causal network where the architecture of reality is constantly being computed and recomputed. The foam has a structure dictated by the unbreakable law of cause and effect. This causal rule is the secret ingredient that tames the wild quantum gravity, preventing it from devolving into total chaos and allowing a sensible universe to form. It suggests that the order we see around us, from the graceful arc of a planet's orbit to the predictable flow of time, is not a given. It is a hard-won achievement, a stable state that has emerged from a whole spectrum of possibilities, all because the fundamental building blocks of everything are compelled to respect a simple, powerful rule: that time has a direction, and that the future is built moment by moment upon the foundation of the past. This journey into the quantum foam inevitably leads us to a profound and disorienting question, one that challenges the very framework of our experience: what happens to time itself? In our daily lives, time is the ultimate constant, an ever-flowing river that carries everything forward with unwavering regularity. But when we descend to the Planck scale, where the geometry of spacetime is a churning, probabilistic foam, this reliable river seems to vanish into a chaotic, directionless sea. This is the infamous problem of time in quantum gravity, and it stands as one of the most significant conceptual hurdles in all of theoretical physics. In Einstein's general relativity, time is woven into the flexible fabric of spacetime as a fourth dimension, but it remains a smooth, continuous parameter. In the standard quantum mechanics that governs particles, time is an external, absolute background against which the drama of wave functions unfolds. But when you try to merge these two theories to describe the quantum foam, this comfortable notion of time completely breaks down. In a realm where the very distinction between here and there is blurred, how can we possibly define a universal now or a consistent before and after? The equations of quantum gravity suggest that at this fundamental level, time, as we understand it, may not exist at all. One compelling resolution to this paradox is the idea that time is not a fundamental ingredient of the universe but an emergent property. Think of temperature. A single molecule doesn't have a temperature. Temperature is a collective property that emerges from the average kinetic energy of trillions of jostling molecules. In a similar way, the smooth, forward-flowing time we experience may be a collective illusion that emerges from the incredibly complex and dynamic interactions within the quantum foam. The spin foam of loop quantum gravity provides a vivid picture of this. Recall that a spin network is a snapshot of space at a single instant. The spin foam is the entire history of how these snapshots evolve. In this framework, there is no external time ticking away in the background. Instead, time emerges from the sequence of changes in the network's configuration. One volume of space changes its quantum state relative to another, and this web of relative changes creates what we perceive as the passage of time. It's a relational concept. Time is not a river we are all floating down, but a story being written by the evolving relationships between every part of the universe. This leads to another radical possibility, that time itself might be granular, composed of discrete, indivisible units. We've already seen how loop quantum gravity suggests that space comes in tiny, finite packets. What if time does too? This concept proposes that there is a smallest possible unit of time, a quantum of time known as the Planck time, which is an astonishing 10 to the power of negative 43 seconds. In this view, the universe does not evolve in a perfectly smooth, continuous flow. Instead, it ticks forward in these incredibly rapid but discrete steps. The smooth flow we experience would be an approximation. Much like the smooth motion of a movie is an illusion created by 24 static frames flashing by every second. At the Planck scale, the universe would be a stop-motion animation of reality, with each frame representing a new configuration of the spin foam. The quantum foam, in its wild fluctuations, would be the director of this cosmic film, determining the probabilistic sequence of each and every frame. But if time is emergent and granular, what gives it its stubbornly consistent forward direction? Why do we remember the past but not the future? This is the puzzle of the arrow of time. In the microscopic world of quantum foam, the fundamental laws are largely time-symmetric. They work the same going forward or backward. Yet, on our large scale, time has a very clear and irreversible direction. The key may lie, once again, in entanglement. As the countless microscopic components of the quantum foam interact, they become increasingly entangled with one another in an ever more complex web of quantum correlations. This growth of entanglement could be the fundamental process that defines the arrow of time. Each new tick of Planck time increases the overall entanglement of the universe, and this process is irreversible. We perceive this constant increase in global complexity as the relentless and unidirectional flow of time from past to future. The reason you can't unbreak an egg is because you can't undo the explosion of quantum entanglement that occurred when it hit the floor. The foam's dynamics are constantly weaving a more complex tapestry of connections, and that weaving only goes one way. Yet for all the explanatory power of the quantum foam, it presents modern physics with perhaps its most embarrassing and profound problem. a numerical catastrophe so severe it threatens to undermine our entire understanding of the cosmos. This is the infamous cosmological constant problem, and it begins with a simple but devastatingly effective calculation. We've established that the quantum vacuum is a frenzied sea of virtual particle pairs constantly flashing in and out of existence. Each of these fleeting fluctuations carries energy. If you take the known quantum fields, the electron field, the quark fields, the fields for all the fundamental forces, and add up the energy from every single possible virtual particle fluctuation throughout all of space, you get a number. And this number, representing the vacuum energy density generated by the quantum foam, is not just large, it is monstrous. The theoretical prediction suggests a level of energy that would cause the universe to expand, or perhaps even to tear itself apart, with such unimaginable ferocity that galaxies, stars, and planets could never have formed. In fact, the calculated value is about 120 orders of magnitude larger than the energy density we actually observe. That's a 1 followed by 120 zeros. It is, quite simply, the worst theoretical prediction in the entire history of science. So what is the cosmological constant, and why does this matter? When Albert Einstein first formulated his equations of general relativity, he found they described a universe that was either expanding or contracting, but not static. Believing the cosmos to be eternal and unchanging, he introduced a fudge factor, a term he called the cosmological constant, to act as a kind of repulsive force that would perfectly balance the inward pull of gravity and keep the universe still. He later called this his greatest blunder after Edwin Hubble discovered the universe was indeed expanding. However, the idea was resurrected in a stunning new form with the discovery of dark energy in the late 1990s. Astronomers found that not only is the universe expanding, but the expansion is accelerating, as if some form of repulsive energy is stretching the very fabric of space. The most straightforward candidate for this dark energy is, you guessed it, the cosmological constant, representing the innate energy of the vacuum itself. But here lies the catastrophic disconnect. The quantum foam calculation gives a value for this constant that is 10 to the power of 120 times bigger than the tiny, gentle nudge we actually see driving cosmic acceleration. Our best theories predict a universe that should have exploded into nothingness instantly, and yet we find ourselves in a cosmos that has endured for billions of years, allowing for the gradual evolution of galaxies and life. Something is profoundly wrong. How could our prediction be so spectacularly incorrect? One possibility is that we are making a fundamental error in how we perform the calculation. The standard method involves summing up all the energies of the virtual particles, but in the bizarre world of quantum field theory, this involves adding up an infinite number of progressively higher energy fluctuations, a process that requires a mathematical trick called renormalization to get a finite answer. Perhaps the assumptions we use in this process are flawed when applied to gravity. Maybe the gravitational field responds to vacuum energy in a way we don't yet understand, effectively cancelling out its own influence. Or perhaps the very concept of summing these energies is misguided, and the vacuum energy of the quantum foam is not a real, gravitating substance in the way we think it is. This line of thinking suggests that the true nature of empty space might be far more subtle, and that the wildly fluctuating energy we calculate is a mathematical artifact rather than a physical reality that can push the universe apart. Another, more radical idea is known as the anthropic principle. This perspective accepts the idea that the cosmological constant could, in theory, take on a vast range of values across a much larger multiverse. In this cosmic landscape, most universes would have a cosmological constant so huge that they either collapse immediately or expand too rapidly for any structure to form. We, of course, find ourselves in one of the exceptionally rare universes where the cosmological constant is minuscule, simply because such a universe is the only kind capable of supporting life that can ask the question, From this viewpoint, the tiny value we observe isn't something we can derive from fundamental theory. It is an environmental selection effect. We are here because the number is small, not the other way around. While this explanation can feel like a cop-out to some physicists, it represents a profound shift in thinking, suggesting that some of the constants of nature may not be fundamental laws but rather local byproducts of our particular cosmic address. A third, and perhaps the most promising, approach involves a principle called supersymmetry. This elegant theoretical framework proposes that every known fundamental particle has a superpartner, a shadow particle with different spin properties. If supersymmetry were an exact, unbroken symmetry of nature, the contributions of virtual particles and their superpartners to the vacuum energy would be exactly equal in magnitude but opposite in sign, resulting in a perfect cancellation that would drive the cosmological constant to zero. The universe would have no net vacuum energy at all. The problem is, we don't see these superpartners in our particle colliders. This means that if supersymmetry exists, it must be a broken symmetry, meaning the superpartners are much heavier than their ordinary counterparts. In this broken state, the cancellation is very, very good but not perfect. It could reduce the vacuum energy by many orders of magnitude, perhaps getting us part of the way toward resolving the discrepancy. While current experiments have not yet found evidence for supersymmetry, it remains a compelling candidate for taming the ferocious energy of the quantum foam and bringing our theoretical predictions closer in line with the serene cosmos we actually inhabit. This relentless churn of the quantum foam, this storm of virtual particles and flickering wormholes, might seem like a self-contained drama playing out on the smallest possible stage. But what if its effects aren't confined to that microscopic realm? What if the ceaseless activity of the foam is actually reaching up, shaping the very fate of the entire cosmos on the grandest of scales? This brings us to a theory that connects the chaotic micro-world directly to the most profound mystery in modern cosmology, the origin of dark energy. The proposal is as elegant as it is staggering. The same vacuum energy that manifests as the Casimir effect and the quantum foam could be the very engine driving the accelerated expansion of our universe. In this picture, dark energy isn't caused by some exotic, unknown substance. It is the quantum foam itself, or more precisely, the innate repulsive pressure generated by its unending activity. To understand how this could work, we need to revisit the nature of the virtual particle pairs we discussed earlier. Each time a pair flashes into existence, it's a tiny, momentary event. But consider the sheer, mind-numbing scale of it. This isn't happening in a few places. It's happening in every single point throughout the entire universe all the time. And while each individual fluctuation is fleeting and localized, their collective effect is to create a constant, pervasive background energy that fills all of space, an energy inherent to the vacuum itself. Now, in Einstein's theory of general relativity, energy and pressure are sources of gravity. Most forms of energy we're familiar with, like matter and radiation, create an attractive gravitational pull which slows down the expansion of the universe. But the peculiar physics of a vacuum fluctuation gives it a very different character. The equations show that this type of energy comes with a strong, intrinsic negative pressure. Think of it not as a substance pushing outward, but as a property of space itself that makes new space. This negative pressure acts as a kind of anti-gravity, causing the fabric of the cosmos to stretch at an ever-increasing rate rather than slow down. Imagine the universe as a loaf of raisin bread rising in the oven. The raisins are galaxies and the dough is the fabric of space. If the dough is just regular dough, it will rise for a while and then stop. But if the dough itself has a special active leavening agent baked into every part of it, an agent that constantly creates more dough, then the loaf will not only keep expanding, but the expansion will speed up over time. The quantum foam is that cosmic leavening agent. Every tiny bubble in the foam, every virtual particle pair annihilating, contributes a minuscule amount of this repulsive push. Individually, each push is insignificant, but collectively, across the vast emptiness of the cosmos, they add up to the smooth, relentless force we call dark energy. The frantic, discontinuous dance at the Planck scale averages out on cosmic scales to become the gentle but unstoppable pressure that is blowing our universe apart. But this elegant idea immediately runs into the same devastating problem we encountered before, the cosmological constant problem. If the quantum foam is the source of dark energy, then our calculation of its energy density is catastrophically wrong. The vacuum energy we predict from the foam should be 120 orders of magnitude stronger than the dark energy we observe. So, how can the foam be the origin of dark energy if our math says it should have torn reality to shreds in the first instant of the Big Bang? This paradox forces physicists to consider more nuanced possibilities. Perhaps only a specific, very low energy component of the quantum foam contributes to the dark energy we see. The ultra-high energy fluctuations might somehow cancel each other out or be inert gravitationally, leaving behind only a faint, residual energy that is driving the acceleration. It's like the hum of a massive, powerful engine. Most of the vibration is dampened and absorbed, and all we feel is a faint, persistent buzz. Another fascinating angle involves the very structure of the foam. Perhaps it's not the raw energy of the fluctuations, but their topology, their shape and connectivity, that generates the repulsive effect. If the quantum foam is a seething soup of tiny, transient wormholes, as John Wheeler suggested, these microscopic structures could be modifying the way gravity works on the largest scales. The collective effect of countless wormholes could be to create a gravitational shielding effect, making the large-scale gravitational pull of the universe appear weaker than it actually is, which would manifest as an apparent cosmic repulsion. In this view, dark energy isn't a force pushing galaxies apart, but a symptom of gravity itself becoming leaky or diluted at cosmic distances due to the foamy, porous nature of spacetime at the microscopic level. The void isn't pushing, it's just that the pull of gravity is being subtly drained away into the foam's intricate architecture. Ultimately, the idea that the quantum foam is the origin of dark energy represents a beautiful, if challenging, unification of the infinitesimally small with the astronomically large. It suggests that the ultimate fate of our universe, whether it continues expanding forever into a cold, dark, and empty future, is being dictated by events happening at a scale we can never directly observe. The same primordial chaos that gave birth to the first particles may now be orchestrating the final act of cosmic evolution. While the catastrophic mismatch in energy density remains a monumental puzzle, it also serves as a blazing signpost telling us that our current understanding of quantum field theory and gravity is incomplete. Solving the riddle of dark energy may not require us to discover a new particle, but to finally decode the true, non-foamy nature of the vacuum itself. The answer is hidden in the quiet hum of nothingness, a hum that is, against all expectation, making the universe scream apart. But to truly push the boundaries of how the quantum foam might operate, we must venture into one of the most audacious interpretations of quantum mechanics, a theory that suggests the flow of time itself might be far more fluid than we perceive. This is the transactional interpretation proposed by physicist John Cramer, and it offers a stunningly different picture of how quantum events become real. In the standard view, a particle like an electron exists as a wave of possibilities until it is measured, at which point its wave function collapses into a definite location. The transactional interpretation replaces this mysterious, instantaneous collapse with a process that is, in a way, more mechanical but also far more strange. It proposes that every quantum event is initiated by a particle sending out a wave into the future, an alpha wave. This wave travels forward in time, exploring all possible paths. But here's the twist. Once it encounters a receiver, like a detector or another particle, the receiver sends a mirror image wave backwards through time, a confirmation wave. Reality in this picture is only established when the original offer wave and the time-reversed confirmation wave find a perfect match and mutually reinforce each other, creating a stable transaction. It's as if the universe is a vast marketplace of potentialities, where deals are only finalized through a handshake that occurs across both the future and the past. Now consider what medium could possibly support such a bizarre two-way street of causation. This is where our journey into the quantum foam provides a compelling stage. The foamy, turbulent structure of spacetime at the Planck scale, with its wormholes and fluctuating geometry, could be the perfect substrate for these advanced waves to travel. If the fabric of reality is not smooth but is instead a complex, foamy network of connections, then the distinction between forward and backward time may become blurred at the most fundamental level. A confirmation wave traveling backwards in time wouldn't need to violate causality in a dramatic way. It could simply be navigating the intricate, non-linear topology of the foam. A microscopic wormhole, for instance, could provide a shortcut that effectively allows information to loop back, creating the transactional handshake that defines a real, observed event. In this view, the quantum foam isn't just a sea of random energy. It's a dynamic communication network that facilitates a continuous dialogue across time, with each settled reality being the result of a successful transaction negotiated through this chaotic medium. This interpretation elegantly explains one of the most famous and weirdest experiments in quantum physics, the double-slit experiment. When particles are fired one at a time at a barrier with two slits, they somehow build up an interference pattern on the far screen, as if each individual particle is passing through both slits simultaneously like a wave. The standard interpretation says the particle exists in a superposition of states, but the transactional interpretation offers a different narrative. The particle emits an offer wave that goes through both slits, interferes with itself, and then travels to the entire detection screen. Every point on the screen is a potential receiver. All of them send confirmation waves back through time. However, only the transaction that results in the most stable, resonant handshake is completed, and that handshake occurs at the specific bright band of the interference pattern where the waves constructively interfere. The particle didn't choose a path. A specific transaction was completed across time, and the foam-like structure of spacetime facilitated that entire non-local process. The observed particle is just the footprint of that finalized agreement. This radical perspective forces us to reconsider the nature of reality on a cosmic scale. If every quantum event is a transaction involving waves from the future, then the entire universe could be seen as a vast, self-consistent network of these completed handshakes. The present moment is not a solitary, moving point on a timeline, but more like a standing wave. A stable pattern formed by the constant, dynamic interplay between the past and the future, all mediated by the quantum foam. This provides a potential, albeit highly speculative, link to the concept of retrocausality, where future events can exert a gentle, sculpting influence on the past. The confirmation waves from potential future outcomes could be subtly guiding the offer waves of the present, shaping the probabilities of what actually happens. The foam, in this grand scheme, is the ultimate arbiter of reality, the chaotic yet law-bound medium that allows the entire universe to consistently and coherently define itself through an endless, silent conversation across time. If you thought the quantum foam was a chaotic environment, prepare for a concept that expands that chaos across an infinite array of realities. The many worlds interpretation of quantum mechanics proposed by Hugh Everett in the 1950s takes the probabilistic nature of the quantum world and gives it the most literal possible meaning. It suggests that every time a quantum system faces a choice like an electron being measured in one of two possible states, the universe doesn't randomly pick one outcome. Instead, it splits. The entire cosmos divides into multiple branches, each one containing a different version of the event unfolding. In one universe, the electron is spinning up, in another, it is spinning down. Every possible outcome that is allowed by quantum probability actually happens, but in a newly created parallel world. Now, connect this breathtaking idea back to the seething quantum foam. If every tiny quantum fluctuation in that foam, every virtual particle pair blinking into existence, every microscopic wormhole forming represents a fundamental quantum event, then according to many worlds, each one of these trillions upon trillions of fluctuations could be a point where reality itself branches. The foam wouldn't just be a sea of energy, it would be the very source code for an ever-expanding, incalculably vast multiverse. This transforms our view of the foam from a turbulent substrate into an active, creative engine. Consider the sheer scale of this activity. In every single cubic centimeter of empty space, at every single moment, an uncountable number of quantum decisions are being made. In the many worlds picture, each of those decisions spawns a new universe. This means the quantum foam is not just churning with energy, it is constantly budding off entire cosmic histories. A fluctuation that creates an electron and a positron for a fleeting moment might, in one branch, see them annihilate as expected. But in another, nearly identical branch, a slight difference in their paths might lead to the electron surviving a fraction of a second longer, setting off a cascade of consequences that, over billions of years, leads to a galaxy forming in a slightly different location. The foam becomes a fractal generator of realities, with every possible variation of physical law and historical event being played out somewhere in the limitless expanse of the multiverse. The gentle hum of the vacuum is in fact the sound of new worlds being born at a rate that defies all human comprehension. What does this imply for our own place in the cosmos? In an infinite multiverse sprouting from the quantum foam, every conceivable version of you likely exists. In one universe, you made a different decision at a pivotal moment in your life. In another, the very laws of physics are different, and life as we know it never formed. This can feel both liberating and deeply unsettling. It resolves the famous paradox of Schrödinger's cat, the thought experiment where a cat in a box is simultaneously alive and dead until observed. In the many worlds view, there is no single spooky collapse of the wave function. There is simply a branching. In one universe, you open the box and find a living cat relieved. In the branch that split off at the very moment the quantum trigger was activated, another version of you finds a dead one. Both outcomes are equally real, and both versions of you are equally conscious, forever unaware of the other's existence. The quantum foam provides the raw material for this endless splitting, its probabilistic nature not being a lack of determinism, but a sign of a reality that is deterministically exploring every single possible path simultaneously. This interpretation also offers a potential solution to one of the great puzzles of cosmology. Why do the fundamental constants of our universe seem so perfectly fine-tuned for the existence of life? If the multiverse is truly infinite, then every possible combination of physical constants and initial conditions exists in some branch. We simply find ourselves in one of the relatively rare universes where the numbers allow for stars, planets, and life to form. There is no deeper reason, it's just a statistical necessity. In this context, the quantum foam is the random number generator for the cosmos. With each fluctuation, it is not only creating particles but rolling the dice on the very laws of physics, spawning universes where gravity is stronger, weaker, or perhaps doesn't exist at all. Our stable, life-friendly universe is just one bubble in a frothing ocean of cosmic possibilities, most of which are utterly barren and alien. The foam's inherent randomness, which once seemed like a problem to be solved, becomes the very mechanism that fills the entirety of existence with every story that can ever be told. But if the quantum foam can generate entire multiverses, could it also offer a spectacular escape from the most absolute prison known to physics, the black hole? Our next theory ventures into the heart of these cosmic monsters and proposes a breathtaking possibility that deep inside a black hole, shielded from our view by the event horizon, the crushing force of gravity does not lead to an infinite abyss, but instead triggers a cosmic rebirth. This idea reimagines the fabled singularity, that point of infinite density predicted by Einstein's equations, not as an end, but as a transition. It suggests that when matter is compressed to the most extreme densities conceivable, the chaotic, discrete nature of the quantum foam steps in to prevent the final collapse, creating a temporary, ultra-dense object known as a Planck star. This isn't a star in the conventional sense, burning with nuclear fusion. It is a star made of spacetime itself, a ball of matter compressed to the Planck density, the maximum allowed by the quantum graininess of the universe. To understand how this works, we need to revisit what happens during gravitational collapse. When a massive star exhausts its nuclear fuel, its own immense gravity causes it to implode. According to classical general relativity, this collapse continues unchecked, crushing all the star's matter into an infinitely small, infinitely dense point, the singularity, where the laws of physics cease to have any meaning. But most physicists suspect that this is a sign that general relativity is incomplete, that it breaks down at such extreme scales and must be replaced by a theory of quantum gravity. This is where the quantum foam and theories like loop quantum gravity come to the rescue. Remember that in LQG, space is not infinitely divisible. It has a fundamental graininess, a smallest possible volume. You cannot compress matter into a volume smaller than one of these fundamental cells. As the collapsing matter approaches this ultimate density, the repulsive forces arising from the quantum geometry become unimaginably powerful. It's as if the very atoms of space are pushing back, creating a titanic pressure that halts the collapse in its tracks. The result is not a singularity, but a Planck star, a ball of matter rebounding at the brink of oblivion. The behavior of this Planck star is as strange as its existence. From the perspective of an unfortunate observer falling into the black hole, the journey would continue inward through the event horizon and toward the ultra-dense core. The formation of the Planck star and its subsequent bounce would happen in a finite amount of their personal time. However, from our perspective outside the black hole, the story is wildly different due to the extreme effects of gravity on time, a phenomenon known as time dilation. As the star forms and begins its rebound, the incredible gravitational field at the event horizon makes this process appear to slow down to a near standstill from the outside. The entire life cycle of the Planck star, its bounce and expansion, would be stretched out over what we would perceive as billions, even trillions of years. To us, the black hole would appear almost unchanging, slowly evaporating via Hawking radiation over cosmic eons. The dramatic rebirth happening inside is a secret kept by the extreme warping of spacetime itself. So, what is the ultimate fate of this rebounding core? The theory proposes that the bounce does not simply lead to the star re-exploding back out into our own universe. That would violate the one-way nature of the event horizon. Instead, the rebound could be so violent that it spawns an entirely new region of spacetime, a new universe. The immense energy of the bounce, channeled through the quantum gravitational foam, could literally puncture a hole in the fabric of our cosmos and initiate a new Big Bang in a disconnected spacetime continuum. In this stunning scenario, every black hole in our universe could be a cosmic womb, a portal to a newborn cosmos with its own physical laws and dimensions. Our entire universe, in turn, might itself be the interior of a black hole existing in a parent universe, part of an infinite fractal tree of cosmic ancestry. The quantum foam in this grand vision is not just the texture of space, but the fertile ground from which entire universes continually blossom. This idea of a white hole, the theoretical time reversed opposite of a black hole, where matter and energy can only pour out, emerges naturally from this picture. The other end of the black hole tunnel wouldn't be a gateway to another part of our universe, but the Big Bang of a new one. While white holes are considered highly speculative and are not observed in our cosmos, they become a compelling description for the birth of a daughter universe. The fireball of the new cosmos, from its own internal perspective, would look just like our own Big Bang, an eruption of space, time, matter, and energy from an initial state of immense density and temperature. The laws of physics in this new universe might be similar to our own, or they could be wildly different depending on the precise quantum fluctuations that were amplified during the bounce. The quantum foam, with its inherent randomness, thus becomes the engine of both cosmic death and creation, a recycling plant for reality itself. The Planck star theory elegantly solves one of the most vexing problems in theoretical physics, the black hole information paradox. If matter falls into a black hole and is lost forever at a singularity, then the information about that matter is irrevocably destroyed. This violates a fundamental principle of quantum mechanics, which states that information must be preserved. However, if the black hole interior contains a bouncing Planck star that eventually transforms into a new universe, the information is not lost at all. It is simply transferred, encoded into the initial conditions of the newborn cosmos. While it might be forever inaccessible to us in our universe, the information is preserved in the larger multiversal structure. The chaotic, information-rich nature of the quantum foam ensures that the cosmic ledger is never unbalanced, even in the face of total gravitational collapse. This paints a universe that is not only stranger than we imagine, but one that is fundamentally resilient, creative, and eternally regenerative, all thanks to the hidden physics operating at the very smallest scales of existence. Now we arrive at a theory that is so elegant and profound it seems to unite two of the most bizarre concepts in physics into a single, breathtaking picture. This is the ER equals EPR conjecture, a proposal that dares to say that the spooky connectedness of quantum entanglement and the fantastical shortcuts of wormholes are not just related, they are two different descriptions of exactly the same thing. To unpack this, we need to look at the two halves of this revolutionary equation. On one side, we have EPR, named for Einstein, Podolsky, and Rosen, who famously pointed out the strange implications of quantum entanglement. This is the spooky action at a distance that so troubled Einstein, where two particles can become linked in such a way that measuring the state of one instantly influences the state of the other, no matter how far apart they are. On the other side of the equation, we have ER, standing for Einstein and Rosen, who together discovered the theoretical basis for wormholes, bridges through spacetime that could, in principle, connect two distant locations. The conjecture, most famously championed by physicists Juan Maldacena and Leonard Susskind, proposes that these two ER concepts are physically equivalent. Every time you have a pair of entangled particles, you are not just seeing a statistical correlation. You are actually looking at the endpoints of a microscopic wormhole woven from the quantum foam itself. This idea transforms our understanding of what entanglement really is. We often picture entangled particles as two separate objects that somehow communicate faster than light. But if ER equals EPR is correct, that picture is fundamentally misleading. The particles aren't communicating across a distance, they are already connected. The space between them is, in a very real geometric sense, an illusion. They are like two different points on the surface of a single, deeper structure, a structure made of spacetime itself. The wormhole, or Einstein-Rosen bridge, connecting them isn't a tunnel you could travel through in the conventional sense. At the quantum scale, it would be a dynamic, unstable feature of the foam, a fleeting tunnel of probabilities that links the two particles directly through the fabric of reality. This provides a stunningly geometric explanation for why measuring one particle seems to instantly affect the other. there is no across for information to travel. The connection is already there, woven into the very geometry of the universe at the Planck scale. The spookiness vanishes, replaced by a tangible, physical link. So, what is the role of the quantum foam in this magnificent unification? The foam is the raw material from which these connections are constantly forming and dissolving. Remember John Wheeler's vision of the foam as a seething sea of virtual particles, microscopic black holes and wormholes. The ER equals EPR conjecture gives a specific, profound purpose to those wormholes. Each one could be the physical manifestation of a quantum entanglement. When two particles become entangled, it's as if a tiny, wormhole-like thread is spun between them from the turbulent energy of the vacuum. This wormhole is not a stable, traversable gateway. It's a quantum entity fluctuating wildly and subject to all the probabilistic rules of the micro-world. Its existence is the entanglement. This suggests that the vast, complex web of quantum correlations that underlies our reality is mirrored by an equally vast and complex network of microscopic spacetime, bridges a cosmic tapestry of connectivity written in the language of geometry. To visualize this, think of the fabric of spacetime as a vast, dynamic sheet. Now take 2 points on that sheet and pinch them together, creating a short, tight loop connecting them underneath the surface. That loop is your microscopic wormhole. The 2 points on the surface are your entangled particles. From the perspective of someone living on the sheet, the 2 points seem far apart. But the hidden connection means they are intimately linked. This changes the very nature of what we call empty space. It's not empty at all. It's a dense, ever-changing network of these tiny filaments of connectivity. The vacuum is less like a still pond and more like a bowl of spaghetti, with countless threads of connection linking every part to every other part. The smooth, classical space we experience is just the calm, average surface of this incredibly intricate and active underworld. The implications of this idea ripple out to touch upon one of the most critical problems in physics, uniting gravity with quantum mechanics. Gravity, in Einstein's theory, is the geometry of spacetime. Quantum mechanics is the theory of particles and fields. ER equals EPR builds a spectacular bridge between them by suggesting that quantum phenomena, specifically entanglement, are themselves manifestations of spacetime geometry. This means that the force of gravity and the weirdness of the quantum world may not be separate things to be reconciled. They may be two different views of the same underlying reality. Where there is geometry, there is gravity, and where there is entanglement, there is geometry. Therefore, the very existence of spacetime and its gravitational field could be an emergent property of a vast network of quantum entanglements. Space itself may not be a fundamental stage, but a tapestry that is woven into existence by these countless quantum threads. We are arriving at a place where the quantum foam is not just the texture of space, but the very mechanism of its creation. This brings us to a dilemma so fundamental it pits our two most successful theories of physics against each other in a battle over the very nature of reality. It's called the black hole information paradox, and it asks a seemingly simple question with an incredibly complex answer. When something falls into a black hole, is the information about that object lost forever? According to Einstein's general relativity, the answer is a grim yes. Anything that crosses the event horizon is irretrievably doomed to travel inward to the central singularity, where it is utterly crushed out of existence. The information that described that object, whether it was a star, a book, or the specific quantum states of a collection of particles, seems to be permanently erased from our universe. But this creates a catastrophic problem for quantum mechanics, which holds the principle of unitarity as sacred. This principle states that information can never be truly destroyed. It can only be scrambled, transformed, or hidden. If quantum mechanics is correct, the information must be preserved somehow. So, where could it possibly be stored if not inside the black hole? one compelling answer lies in the chaotic, information-rich nature of the quantum foam itself. The paradox was thrown into sharp relief by Stephen Hawking's groundbreaking work in the 1970s. Hawking demonstrated that black holes are not completely black. Due to quantum effects occurring just outside the event horizon, they slowly radiate energy, a phenomenon we now call Hawking radiation. Here's how it works. Remember the virtual particle pairs that constantly flicker in and out of existence in the quantum foam. Imagine this happening right at the precipice of a black hole's event horizon. Occasionally, one particle of the pair will fall into the black hole while its partner escapes into space. From our perspective, the black hole has just emitted a particle. To conserve energy, the particle that fell in must have negative energy, which causes the black hole to lose a tiny amount of mass. Over astronomical timescales, this process causes the black hole to evaporate completely. The problem is, the Hawking radiation that escapes appears to be completely random, a featureless thermal glow that carries no information about what fell into the black hole. So, if the black hole evaporates entirely, leaving behind only this random radiation, the information about everything it ever consumed seems to have vanished from the universe, violating a core tenet of quantum theory. This is where the quantum foam offers a potential escape route. The key might be that the event horizon is not a perfectly smooth, calm boundary as classical physics suggests. Instead, it must be a region of unimaginable activity, a seething layer of quantum foam where spacetime is wildly fluctuating. As matter and information cross this boundary, they don't simply vanish from existence. Instead, their information could be imprinted or encoded onto this frenetic, two-dimensional surface of the horizon. Think of it like a cosmic scratch pad, but one with an almost infinite storage capacity. Every particle, every bit of information that falls in, could leave a tiny holographic imprint on the event horizon's foam-like structure. This idea aligns with the holographic principle we discussed earlier, where all the information within a three-dimensional volume can be stored on its two-dimensional boundary. In this view, the black hole doesn't destroy information. It stores it in the most efficient way possible on the vibrant, foamy surface of its event horizon. But how does that stored information ever get out? The proposal is that it is slowly and meticulously released in the Hawking radiation itself. Even though this radiation appears random and thermal to a casual observer, its precise details could be subtly influenced by the information encoded on the horizon. The fluctuations in the quantum foam at the event horizon would imprint tiny correlations onto the escaping radiation particles, a complex code that, in principle, contains the entire history of the black hole's diet. Decoding this information from the radiation would be a task of almost impossible difficulty, like reconstructing a burned book from the pattern of smoke and ash it produced, but the information would not be gone. It would be transformed, preserved in the intricate tapestry of the radiation, ensuring that the universe never forgets what was lost. The quantum foam, in this scenario, acts as both the scrambler and the preserver of information, a chaotic but lawful librarian for the cosmos. A different but equally fascinating solution to the paradox completely reimagines what a black hole actually is. This is the fuzzball proposal from string theory. It does away with the concept of a vacuum-filled interior and a smooth event horizon altogether. Instead, it suggests that a black hole is a giant, tangled ball of strings and brains, a fuzzball that is bursting with information and has no central singularity. The entire volume of the black hole is filled with this incredibly complex quantum mechanical structure, and its surface is a fuzzy, foamy boundary where the fundamental strings of reality end. There is no inside to fall into in the traditional sense. An object falling into the black hole would simply merge with this giant fuzzball. Its information instantly spread throughout the entire structure, much like a drop of ink dispersing in a glass of water. In this picture, the quantum foam isn't just a skin on the horizon, it is the black hole. the entire object is a manifestation of the foam's most extreme and organized state. The fuzzball resolves the information paradox by eliminating the two features that created it, the smooth event horizon and the destructive singularity. Since there is no point of infinite density where information is erased, and since the horizon is a tangible, information-saturated surface, the information is always preserved within the total quantum state of the fuzzball. Hawking radiation in this model is not a random process pulled from the vacuum. It is emitted directly from the vibrant, hot surface of the fuzzball itself. Because the radiation originates from this complex, information-rich structure, it naturally carries that information with it as the black hole evaporates. The paradox simply evaporates along with the black hole. This presents a universe where black holes are not ultimate prisons, but the most densely packed libraries of information in existence, their foamy, fuzzy nature safeguarding the quantum coherence of the cosmos against total erasure. Whether the information is stored on a holographic, foamy horizon or within a massive fuzzball, both ideas point to a universe that is fundamentally preservative, not destructive. The resolution of the black hole information paradox suggests that reality, at its heart, respects the past. It keeps a record. The seemingly mindless chaos of the quantum foam may, in fact, be the mechanism that ensures no story, no particle, and no event is ever truly forgotten. It is the ultimate cosmic archive operating at the very edge of spacetime, ensuring that even in the face of total gravitational collapse, the ledger of the universe remains forever balanced. And so we arrive at a theory that challenges our most basic intuition about the very stage upon which reality plays out the idea that space is made of distinct, mappable points. What if, at the most fundamental level, the concept of a precise location simply ceases to exist? This is the startling proposition of non-commutative geometry, a framework that applies the bizarre logic of quantum mechanics to the coordinates of spacetime itself. We are all familiar with the quantum uncertainty that says you cannot know both a particle's exact position and its exact momentum at the same time. Non-commutative geometry takes this principle of fuzziness and applies it directly to the fabric of the cosmos. It suggests that the very coordinates that label points in space do not commute. In simple terms, this means that measuring one spacetime coordinate interferes with the measurement of another. To grasp this strange idea, imagine trying to pinpoint a location on a microscopic grid. You might think you could simply measure its east-west position and then its north-south position to get a perfect fix. But in a non-commutative world, the order in which you take these measurements matters profoundly. If you measure the east-west coordinate first and then the north-south, you get one result. But if you reverse the order, measuring north-south before east-west, you get a slightly different location. The two operations do not commute. They cannot be swapped without changing the outcome. This inherent fuzziness means that at the Planck scale, the universe resists being pinned down to a single mathematical point. Locations are inherently smeared, blurring into one another like a photograph taken with a shaky hand. The sharp, well-defined grid of classical physics dissolves into a probabilistic, foamy geometry where the very notion of here becomes a matter of quantum probability. This blurring of points has a direct and dramatic consequence for the quantum foam. If you cannot define a perfect point, then you cannot have a perfectly smooth, continuous geometry. Instead, the fabric of spacetime must take on a granular, foamy texture. Think of it like the grain in a piece of wood or the pixels on a digital screen. But this is a far more profound kind of graininess. It's not that space is made of tiny, solid blocks that you could, in theory, count. The fuzziness is fundamental and unavoidable, woven into the very act of measurement. In this picture, the wild fluctuations of wormholes and virtual particles that John Wheeler envisioned are not just happening in space. They are the manifestation of this non-commutative, fuzzy reality. The foam is the visual and physical expression of a world where the coordinates themselves are dancing to a quantum tune, refusing to sit still long enough to be precisely defined. This perspective also offers a fresh way to think about the unification of all fundamental forces. In our everyday experience, gravity is the curvature of smooth space-time, while the other forces, electromagnetism and the nuclear forces, are described by quantum fields that live on that space-time stage. This separation is the central obstacle to a complete theory of quantum gravity. Non-commutative geometry proposes a breathtakingly elegant solution. What if gravity and the other forces are all manifestations of the same underlying fuzzy geometry? In this framework, the force fields for particles like electrons and quarks are not separate entities inhabiting space. They emerge naturally from the non-commutative properties of spacetime itself. The smearing of points creates a rich, complex geometry that naturally includes what we perceive as forces and matter. Gravity is no longer a special case. It is simply part of the overall, fuzzy geometric package. The churning quantum foam isn't just the home of gravity, it is the unified source of all physics. To visualize this, picture a calm, flat pond. This is our classical view of space. Now, imagine the surface of that pond is actually made of a strange, intelligent gel that resists being poked at a single point. The more you try to pinpoint a specific location on its surface, the more the entire surrounding area jiggles and deforms. Your attempt to measure one coordinate inevitably disturbs the others. The entire surface is alive with this inherent, restless activity. This is the non-commutative geometry of spacetime. The foam is that constant, low-level jiggling, the fundamental fuzziness that is the true nature of the gel. And just as waves and ripples can travel across the pond's surface, the particles and forces we observe could be specific, stable patterns of excitation moving through this fuzzy, gelatinous medium. The electron isn't a tiny ball sitting on the gel. It is a self-sustaining vibration of the gel itself, its properties determined by the gel's inherent non-commutative rules. Ultimately, non-commutative geometry presents a universe that is profoundly relational and interactive. It tells us that we cannot be passive observers of a pre-existing, rigid stage. The very act of observation of measurement is an interaction that forces the fuzzy, foamy reality to crystallize into a specific, though imprecise, outcome. This theory doesn't just add quantum foam to the background of reality. It argues that the foam is the reality, a direct consequence of the fact that the universe's most basic coordinates refuse to be tamed. It is a vision where the cosmos is built not from points and lines, but from a web of uncertain relationships, a dynamic and fuzzy tapestry from which everything we know and are ultimately emerges. But if the universe's deepest workings are rooted in a fuzzy, non-commutative foam, what is the fundamental substance that is actually doing the fluctuating? This brings us to one of the most ambitious and mathematically beautiful frameworks in all of physics, string theory, and its quest to become a final theory of everything. For centuries, we have described the fundamental constituents of matter as point-like particles, infinitely small, zero-dimensional dots. This picture has been incredibly successful, but it also leads directly to the intractable infinities and paradoxes we encounter when trying to merge gravity with quantum mechanics. String theory makes a breathtakingly simple yet profound shift in this paradigm. It proposes that the most basic building blocks of nature are not zero-dimensional points, but incredibly tiny, one-dimensional loops of energy strings. These strings are so minute that if an atom were enlarged to the size of our solar system, a string would be about the size of a single tree on Earth. And just like the strings on a violin, they can vibrate. The power of this idea lies in those vibrations. A violin string can vibrate in different modes to produce a wide range of notes, a G, a D, an A. In exactly the same way, a fundamental string in this theory can vibrate at different resonant frequencies. And here is the miracle. Each distinct vibration pattern corresponds to a different kind of particle. One specific resonance might manifest as an electron. Another, slightly different vibration might become a quark. Another still could be a photon, the particle of light. In this elegant scheme, the bewildering zoo of subatomic particles we have discovered in particle accelerators is not a collection of different fundamental objects. Instead, it is a symphony played on a single type of instrument, the string. The properties of each particle, its mass and its charge, are determined by the precise note its string is playing. This includes the most elusive particle of all, the graviton, the hypothetical quantum particle that carries the force of gravity. For the first time, gravity emerges naturally from a quantum mechanical framework, not as an external force, but as another note in the cosmic symphony. However, for this mathematical symphony to be consistent, it demands a very specific kind of stage, one with more dimensions than the three of space and one of time that we experience. The equations of string theory only work in a universe with 10, or in some versions, 11 dimensions. This immediately raises a perplexing question. If there are extra dimensions, where are they? Why don't we see them? The compelling answer is a process known as compactification. The theory suggests that these extra dimensions are not vast, expansive realms like our own. Instead, they are curled up or compactified into an unimaginably tiny, complex shape at every single point in our familiar four-dimensional spacetime. To visualize this, think of a long, thin garden hose. From a distance, it looks like a simple one-dimensional line. But if you get very close, you see that it actually has a second dimension, a circular cross-section curled up into a tiny loop around its length. In the same way, at every point in our four-dimensional universe, there could exist 6 or 7 extra spatial dimensions, curled up into a fantastically intricate microscopic shape called a Calabi-Yau manifold. This is where the quantum foam re-enters the narrative in a spectacular fashion. The process of compactification isn't necessarily smooth or predetermined. The extra dimensions could be dynamically stabilized by the same frenetic energy that characterizes the quantum foam. Imagine the compactified dimensions as tiny, hyperdimensional spheres or loops that are constantly trying to expand or contract due to their own internal forces. However, the relentless fluctuations of the foam, the virtual particles and gravitational waves buzzing at the Planck scale, could act as a stabilizing pressure. It would be like a multitude of tiny, invisible hands constantly patting and shaping these extra dimensions, holding them in their compactified form against the forces that would otherwise cause them to unravel. The specific, stable configuration of these extra dimensions, dictated by the foam's dynamics, would then determine the very laws of physics in our observable universe. The masses of electrons, the strength of the nuclear forces, and the existence of atoms themselves would all be contingent on exactly how the quantum foam has frozen into a particular stable pattern for the extra dimensions. This leads to a staggering implication. The universe we inhabit may not be unique. String theory, combined with the dynamics of the foam, suggests the existence of a vast landscape of possible universes. Each point in this landscape corresponds to a different way for the extra dimensions to be curled up and stabilized. In each of these different configurations, the resulting effective laws of physics would be different. In most of these universes, the constants might be such that atoms are unstable, stars cannot form, and life is impossible. We find ourselves in one of the rare habitable pockets where the numbers work out, not because of a grand design, but simply because our particular quantum foam fluctuation allowed for it. In this view, string theory does not predict a single unique universe, but a multiverse of breathtaking diversity, with the quantum foam acting as the ultimate architect, randomly crystallizing different physical realities from a spectrum of mathematical possibilities. The search for a single, elegant theory of everything thus transforms into a cosmic census of possible realities, with our own existence being a testament to one particularly fruitful fluctuation in the primordial foam. But if the quantum foam is a frenzied sea of information, what is it actually doing with all of it? This leads us to a theory that proposes the cosmos is not just a place but a process, a continuous, ongoing computation. Imagine the universe itself as the most powerful quantum computer imaginable, and the quantum foam is its processor. In this breathtaking view, every fluctuation, every virtual particle pair, and every microscopic wormhole is not a random event, but a fundamental operation in a cosmic calculation. The very laws of physics, from the gentle fall of an apple to the fierce fusion in a star, are not static rules but emergent algorithms, the output of this relentless, universe-wide computation happening at the Planck scale. Reality in this paradigm is not made of stuff but of information being processed. What we perceive as matter and energy are simply stable, persistent patterns of data in this unimaginably vast computation. To grasp this, we need to understand the basic unit of this cosmic computer, the qubit or quantum bit. Unlike a classical computer bit, which can only be a 0 or a 1, a qubit exists in a superposition of both states simultaneously. It's only when the qubit is measured that it settles into a definite value. Now, envision the quantum foam as an incalculable number of these qubits, each one represented by a fundamental degree of freedom in the fabric of spacetime, perhaps the spin of a loop-in-loop quantum gravity, or the state of a tiny patch of a Calabi-Yau manifold in string theory. These qubits are constantly interacting, entangling, and processing information according to the universe's underlying quantum software, the laws of physics. Each Planck-sized tick of time is a processing cycle where the entire network of qubits updates its state, moving the cosmic computation forward one infinitesimal step. How does this abstract computation give rise to the world we see? Think of a complex video game. The world you explore on your screen seems solid and continuous, but beneath the surface, it's all being generated by the relentless calculations of a computer's processor, updating the state of millions of pixels dozens of times per second. In the cosmic analogy, the smooth, continuous reality of stars and planets is the high-resolution display. The frantic, discrete calculations of the quantum foam are the hidden hardware and software. When a virtual particle pair flashes into existence, it's not merely a random energy fluctuation. It could be the execution of a specific logical operation. The entanglement between two distant particles isn't spooky action at a distance. It's a logical correlation established between two qubits in the cosmic processor. The entire evolution of the universe, from the Big Bang to the present, is simply the execution of a single, immensely long-running program. One of the most compelling proponents of this idea was the late physicist John Archibald Wheeler, who famously coined the phrase "it from bit." For Wheeler, this was a profound philosophical stance. The "it" refers to all physical things, particles, fields, forces. The "bit" refers to information. His radical proposal was that every piece of the physical world ultimately derives its existence from binary yes or no questions, from bits of information. In the context of the quantum foam, this means that the answer to a fundamental yes or no question, like, is there a wormhole connecting these 2 points? Or did a virtual particle appear at this location? Is what actually constructs spacetime and everything in it. The universe is participatory. The act of posing these questions and receiving answers through quantum measurement is what brings reality into being. The foam is the dynamic medium where these cosmic questions are constantly being asked and answered. This perspective offers a fresh and powerful way to think about one of physics' greatest challenges, the unification of general relativity and quantum mechanics. General relativity is a supremely elegant theory of the macro world, describing the smooth, deterministic geometry of spacetime. Quantum mechanics is the wildly successful but bizarre theory of the micro world, dealing in probabilities and uncertainties. In the computational universe model, this divide makes perfect sense. The smooth geometry of general relativity is the user interface, the high-level, emergent reality that we interact with. The probabilistic, quantized quantum world is the machine code, the fundamental, discrete level of processing that generates that interface. The quantum foam is the central processing unit where this translation happens. The weirdness of quantum mechanics, with its superpositions and collapses, is simply a reflection of how this ultimate computer operates at its most basic, logical level. But who or what is programming this cosmic computer? The theory offers several possibilities, none less staggering than the next. One is that the universe is simply running a predetermined program, its initial conditions set at the Big Bang. Another, more mind-bending possibility is that the universe is a self-organizing learning system. Its laws are not fixed but are algorithms that can evolve over time, optimizing for stability and complexity. The most radical idea is that our universe is a simulation running on a computer in a higher-level reality. While this can sound like science fiction, it's a hypothesis some physicists and philosophers take seriously. If true, the quantum foam would be the fundamental substrate of the simulation, the base reality of the simulator. The Planck length would be the pixel size, and the speed of light would be the processor's clock speed, a limit on how quickly information can be updated across the cosmic grid. While we may never be able to prove this, the very fact that our universe appears to be computable, that its laws can be expressed as mathematical relationships, is a tantalizing clue. Ultimately, viewing the quantum foam as a quantum computer transforms our quest for knowledge. We are no longer just trying to discover the laws of physics. We are, in effect, trying to reverse engineer the universe's operating system. Every experiment in a particle accelerator is a probe into the cosmic processor's logic. Every observation of a distant galaxy is a readout of the cosmic program's output. This framework doesn't diminish the wonder of existence, it amplifies it. The majestic spiral of a galaxy and the intricate structure of a snowflake are not just beautiful accidents, but magnificent and complex patterns emerging from the sublime, underlying computation of reality itself, processed one quantum bit at a time in the churning, foundational foam of spacetime. Yet for all its potential to connect and create, the quantum foam may also contain a set of cosmic safety protocols, a set of fundamental laws designed to protect the integrity of reality itself from its own most dangerous possibilities. This brings us to a fascinating and pivotal proposal from Stephen Hawking, known as the chronology protection conjecture. Hawking was famously skeptical about the possibility of time travel to the past, not merely because it seemed technologically fantastical, but because it created insurmountable logical paradoxes. What happens if you go back in time and prevent your own grandparents from meeting? The very consistency of cause and effect, the logical foundation of the entire universe, would unravel. Hawking wryly noted that we never see tourists from the future, suggesting that time travel is simply impossible. His conjecture provides a specific, physics-based mechanism for why it must be impossible. The laws of physics, he argued, act as a cosmic sensor, protecting the timeline from paradoxes, and the mechanism for this protection is likely found in the frenetic energy of the quantum foam. To understand how this works, we need to revisit the idea of a wormhole time machine. A stable, traversable wormhole, if one could exist, would not only connect two distant points in space, but could also connect two different moments in time. By manipulating one mouth of the wormhole, perhaps by taking it on a journey at near light speeds and then bringing it back, you could create a time difference between the two ends. One mouth would be in your present, while the other mouth would open into your past. You could then, in theory, walk through the wormhole and emerge at a moment before you even entered it. It's a concept that has fueled countless science fiction stories, but according to Hawking's conjecture, the universe's own fundamental nature has a built-in fail-safe to prevent this exact scenario. The moment you try to set up such a paradoxical loop, the quantum foam surrounding the wormhole would react with catastrophic violence. The engine of this destruction is a phenomenon known as vacuum polarization. In the calm, flat spacetime of our everyday experience, the virtual particle pairs of the quantum foam appear and annihilate in a balanced, self-canceling dance. But when spacetime is bent into the extreme geometry required for time travel, this delicate balance is shattered. As a particle travels through a wormhole and back into its own past, its own presence creates a feedback loop. Imagine the ghost of a single photon. In a stable, non-time traveling wormhole, it might pass through once and be gone. But in a wormhole configured as a time machine, that same photon could exit the wormhole in the past, travel through space, and then re-enter the wormhole at the very same moment it originally departed. It would meet its past self and then do it again and again. The particle isn't being cloned, it's the same particle, trapped in an endless cycle where it continuously interacts with its own history. This is where the quantum foam enters the picture with devastating effect. The vacuum isn't truly empty, it's filled with these virtual particle fluctuations. In the region of spacetime warped to form a closed time-like curve, the technical term for a path through space that loops back in time, these virtual particles can also get caught in the same kind of feedback loop. A single virtual particle pair could appear, and one particle could get swept into the time-traveling path. It would then loop back and interact with its own recent past, influencing the very conditions of its own creation. This self-interaction causes the energy of the fluctuation to be amplified with each cycle. The calculation shows that the energy density of the vacuum in the region of the time machine wouldn't just grow, it would skyrocket toward infinity in an impossibly short amount of time. The vacuum fluctuations would blow up, becoming infinitely large, and this infinite energy would catastrophically warp spacetime itself, likely causing the nascent wormhole to collapse into a singularity or simply disintegrate long before any macroscopic object, let alone a human time traveler, could ever hope to pass through. Think of it like an audio system with a microphone placed too close to a speaker. The quietest sound from the room is picked up by the microphone, amplified through the speaker, then picked up again by the microphone and amplified even more. In an instant, this feedback loop creates an ear-splitting, destructive screech. The chronology protection conjecture suggests that spacetime itself has a similar kind of gain control. The quantum foam provides the background, hiss, and the closed time-like curve provides the feedback loop. The moment the time machine is switched on, the system is driven to a catastrophic volume, an infinite energy density that destroys the amplifying mechanism, which in this case is the wormhole. The universe, in essence, screeches in protest and shuts down the paradoxical circuit before it can be completed. The foam acts as both the censor and the enforcer, a chaotic but law-abiding police force that maintains the causal order of reality. This conjecture highlights a breathtakingly elegant feature of our cosmos, its profound tendency toward self-consistency. The laws of physics seem to be designed in such a way that they prevent logical contradictions from ever occurring. It's not that a time traveler would be forbidden from changing the past. The laws of physics make it impossible to even construct the apparatus needed to make the attempt. The quantum foam, often depicted as the realm of ultimate chaos and randomness, is here revealed as the guardian of cosmic order. Its wild, probabilistic nature, which allows for fleeting wormholes and fluctuations, also contains the seeds of their immediate destruction if they ever threaten to destabilize the flow of cause and effect. In this light, the foam is not just a creative substrate, but also a deeply conservative one, preserving the linear narrative of the universe against the threat of paradoxical loops. The very same feature that makes the vacuum a seething sea of potential also makes it an impassable barrier against anyone who would seek to unravel time itself. We have explored how the quantum foam might stabilize extra dimensions and even act as a cosmic computer. But what if its most famous role as the source of gravity has been completely misunderstood? This brings us to a theory so radical it reimagines one of the most familiar forces in the universe as a grand and powerful illusion. For centuries, since the time of Newton, we have thought of gravity as a fundamental force, an invisible pull that acts across vast distances. Einstein refined this picture, describing gravity not as a force but as the curvature of spacetime itself, a geometric warping caused by mass and energy. But physicist Eric Verland has proposed a third, even more profound perspective. Gravity is not fundamental at all. It does not exist as a basic ingredient of the universe. Instead, gravity emerges. It is a side effect, a consequence of something much more primitive, the tendency for disorder or entropy to increase. And the stage for this incredible emergence is none other than information stored in the microscopic structure of the quantum foam. To grasp this mind-bending idea, we first need to understand entropy. In thermodynamics, entropy is a measure of disorder, of the number of ways a system's microscopic components can be arranged while still looking the same from a macroscopic view. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. A classic example is a drop of ink in a glass of water. Initially, the ink is concentrated, a state of low entropy, but it quickly disperses, spreading out evenly throughout the water. This mixed state is one of high entropy. There are vastly more ways for the ink molecules to be spread out than to be bunched together in a single spot. The system naturally evolves toward this maximum disorder. Verland's genius was to ask, what if this same principle, this drive toward higher entropy, is what we feel as gravity? Imagine the universe as being made of fundamental bits of information. Think of the quantum foam as a vast storage medium, with every tiny bubble or fluctuation representing a single bit. Now place a massive object like a star into this sea of information. The presence of the star displaces the quantum foam, much like a heavy object placed on a mattress displaces the stuffing inside. This displacement changes the arrangement of the information in the foam around the star. According to Verland, gravity arises when these microscopic bits of information rearrange themselves to maximize their entropy. The natural tendency for the information to become more disordered manifests as an apparent force that pulls objects together. It's not that the star is actively pulling on a planet. It's that the entangled information in the quantum foam is redistributing itself, and this redistribution pushes the planet toward the star in the same way that the ink drop is pushed to spread out in the water. Gravity, in this view, is an entropic force. Let's make this more concrete with a startling analogy. Consider a polymer like a strand of DNA floating in a bath of water. If you try to squeeze the polymer into a very small space, you are reducing the number of ways the water molecules can be arranged around it. You are decreasing the system's entropy. The polymer will push back, not because of a fundamental repulsive force in its chemical bonds, but simply because the entire system is fighting to return to a state of higher disorder. This pushing is an entropic force. Verland suggests that gravity works in a remarkably similar way. When two masses are far apart, the quantum foam around them has a certain number of microscopic configurations. When you bring them closer together, you actually reduce the number of possible ways the information in the surrounding foam can be arranged. The system resists this reduction in entropy, and that resistance is what we perceive as an attractive force between the masses. The universe is effectively saying, I have more ways to be disordered if these objects are closer together, and it pushes them toward each other to achieve that state. So, what is the specific role of the quantum foam in this entropic gravity? The foam is the fundamental substrate where the information about the location of energy and matter is stored. In Verland's framework, space itself is built out of a network of entangled quantum bits. The frothing, dynamic activity of virtual particles and microscopic wormholes isn't just random noise, it is the physical manifestation of this information processing and storage. The foam's structure encodes the microstates of space. When a mass is present, it alters the entanglement relationships between these bits, essentially imposing a new set of rules on how the information can be arranged. The emergent force we call gravity is then a direct result of the foam's tendency to evolve toward the configuration with the highest possible entropy, given these new constraints. The foam isn't just the arena for gravity. Its intrinsic properties and the laws of information theory are what generate the gravitational interaction from the ground up. This perspective offers a breathtakingly elegant solution to one of the most perplexing mysteries in modern cosmology: dark matter. We observe that galaxies rotate much faster than they should based on the amount of visible matter they contain. The standard solution is to propose the existence of vast amounts of invisible, non-luminous dark matter that provides the extra gravity. But what if there is no dark matter particle? Verland's theory of emergent gravity provides an alternative. In his equations, the ordinary visible matter in a galaxy modifies the entropy content of the surrounding quantum foam. This modification, in turn, creates an additional gravitational effect that is not accounted for in Newton's or Einstein's laws. This extra push from the entropic force precisely mimics the gravitational pull we would expect from a halo of dark matter. In other words, dark matter might not be a substance at all, but a signature of the way gravity emerges from the quantum information stored in the foam. We aren't seeing the effects of invisible matter, we are seeing the effects of the universe's innate tendency toward disorder on a galactic scale. The implications of this idea reach to the very heart of theoretical physics. If gravity is emergent, then the search for a quantum theory of gravity, a theory that describes gravity in the same quantum mechanical language as the other forces, takes on a completely new character. We wouldn't be looking for a graviton particle in the same way we found the photon. Instead, the graviton would be a kind of collective excitation, an emergent phenomenon from the underlying network of entangled information, much like a sound wave is an emergent phenomenon from the collective motion of atoms in a crystal. The smooth, geometric spacetime of general relativity would be a kind of thermodynamic, large-scale approximation of the frantic, informational activity of the quantum foam. This would beautifully resolve the tension between gravity and quantum mechanics, not by quantizing spacetime, but by showing that spacetime and its gravitational field were never fundamental to begin with. They are both secondary features of a deeper, information-theoretic reality. Verland's vision of emergent gravity presents a cosmos that is fundamentally holographic and computational. The universe is not a collection of things interacting through forces, but a dynamic system of information that evolves according to statistical rules. The force that holds our feet on the ground and guides the planets in their orbits is not a primary law, but a secondary consequence, a sort of cosmic peer pressure exerted by countless microscopic bits of information in the quantum foam, all striving for maximum disorder. This transforms gravity from a mysterious, fundamental pull into a statistical tendency, an irresistible drift toward a state of higher entropy that we, from our limited perspective within the system, experience as an attractive force. It suggests that the most familiar force in our daily lives is in fact the most profound illusion, a ghostly echo of the hidden informational engine that is the true fabric of reality. While many of the theories we've explored treat the quantum foam as a chaotic but fundamental layer of reality, a profoundly different vision was offered by the brilliant and unconventional physicist David Bohm. He saw the foam not as the basement of existence, but as a surface ripple on a much deeper, more mysterious ocean. Bohm proposed that our entire universe of separate objects and events, the world we see and touch, is an explicate order, a kind of projection or unfolding from a hidden, underlying reality he termed the implicate order. In this view, the frenetic dance of the quantum foam and everything within it are not the primary actors in the cosmic play. They are merely the unfolding manifestation of a far richer, more interconnected, and deeply enfolded whole. To grasp this radical idea, consider the humble hologram. When you look at a holographic film plate, it appears to be nothing more than a meaningless pattern of swirls and interference lines. Yet, when you shine a laser through it, a full, three-dimensional image magically appears in space. The entire three-dimensional structure is somehow encoded or enfolded into every single region of the two-dimensional plate. If you were to cut the plate into tiny pieces, you would find that each fragment, when illuminated, still contains the entire image, albeit with less resolution. Bohm suggested that reality works in a similar way. The entire cosmos, past, present, and future, is enfolded into the implicate order. Our experience of a world with distinct objects located in specific places is the result of this order unfolding into the explicate reality we perceive. The quantum foam, with its non-local connections and blurred distinctions, could be seen as a direct glimpse into this process of enfoldment and unfoldment, a place where the seamless wholeness of the implicate order is just barely visible through the cracks of our explicate world. Bohm gave a powerful name to the dynamic process by which the implicate order constantly unfolds into the explicate and then re-enfolds back into the whole, the holomovement. This isn't a movement through space and time, but a deeper, more primary movement of space and time themselves. It is the continuous, unbroken flow of reality, a ceaseless process of creation and dissolution. In this framework, a subatomic particle isn't a tiny, solid ball. It is a relatively stable, persistent manifestation of the holomovement, a tiny whirlpool in a flowing river. The whirlpool has a distinct and recognizable form, but it has no independent existence from the river. It is sustained by the constant flow of water, and if the flow stops, the whirlpool vanishes. Similarly, the electron or quark is a temporary, stable feature of the holomovement, its properties defined not by its own isolated nature, but by the entire, unbroken flow of the cosmos from which it emerges. This perspective completely reframes the bizarre phenomenon of quantum entanglement. In the standard interpretation, two entangled particles influencing each other instantly across vast distances seems like spooky action at a distance. But for Bohm, this wasn't spooky at all. It was evidence for the implicate order. In the explicate realm, the particles appear separate, but in the deeper implicate order, they are not two distinct things that need to communicate. They are fundamentally non-local, arising from the same underlying ground of reality. Their connection is not transmitted across space. It is a reflection of their shared origin in the holistic implicate order. The apparent separation is the illusion, a temporary unfolding, while their profound connectedness is the deeper truth. The quantum foam, then, with its web of potential wormholes and instantaneous correlations, is not a computational grid but a physical expression of this fundamental non-separability, the tangible signature of the holomovement at the smallest scales of the explicate world. So, what does the implicate order consist of? Bohm did not see it as a realm of particles or fields in any conventional sense. He described it as a realm of potentiality, a vast ocean of active information. He used the analogy of a drop of ink squeezed into a viscous fluid like glycerin. If you place the drop in the fluid and then slowly rotate the container, the ink will be drawn out into a fine, thread-like filament, eventually becoming so spread out that it becomes invisible to the naked eye. The ink has been enfolded into the fluid, yet if you then rotate the container in the reverse direction, the entire process will unwind and the drop of ink will miraculously reassemble itself. The information needed to reconstruct the drop was never lost. It was simply hidden within the overall state of the system. The implicate order is like that fluid, and every object in our universe is like that drop of ink, a temporary, unfolded manifestation of information that is always part of the whole. This philosophical framework offers a powerful way to understand the role of the observer in quantum mechanics. The famous collapse of the wave function is not, in Bohm's view, a random or mysterious event. It is the moment when a specific potentiality from the implicate order is actualized into the explicate order through the interaction of the entire experimental context, including the measuring device and the conscious observer. The holomovement brings a particular aspect of its infinite potential into tangible reality. This resolves the paradox of Schrödinger's cat not by splitting universes or invoking backward-traveling waves, but by suggesting that the cat's alive and dead states are both enfolded potentials. The act of observation is not a passive recording but an active participation in the holomovement, a moment where the universe unfolds a specific storyline from its vast repertoire of possibilities, guided by the total context of the situation. We are not outside observers of the cosmos, we are intimate participants in its endless, unfolding dance. But this seamless coordination between the observer and the observed leads us directly to one of the most stubborn and profound mysteries in all of science, the measurement problem. Why is it that a quantum system, which can exist in a shimmering cloud of overlapping possibilities, suddenly snaps into one single, definite reality the moment we look at it? For decades, the standard textbook explanation has been the collapse of the wave function, a mathematical rule that tells us the probability of each outcome, but offers no physical mechanism for how this magical transition from maybe to is actually occurs. It simply happens. This has led many physicists to wonder if this collapse isn't just a convenient calculation tool, but a real physical event, and that the turbulent medium of the quantum foam might be the very stage where this drama unfolds. One compelling theory that takes this idea seriously is known as objective collapse. Proponents of this view argue that the wave function collapse is not triggered by the vague and mysterious act of measurement, but by a specific physical process that occurs spontaneously in nature. The most famous of these models is the Garadi-Rimini-Weber, or GRW, theory. It proposes that every particle has a tiny but finite probability of spontaneously collapsing its wave function at any given moment. For a single electron, this spontaneous collapse would be exceedingly rare, perhaps happening only once every 100 million years. But in a macroscopic object like a cat or a measuring device, which contains trillions upon trillions of particles, the probability that at least one of them will collapse becomes a near certainty in a tiny fraction of a second. The collapse of one particle then triggers a domino effect, forcing the entire system to snap into a definite state almost instantly. But what could be the physical trigger for these spontaneous collapses? This is where the quantum foam enters the picture. The relentless, chaotic fluctuations of the spacetime foam could provide a constant, low-level background noise that literally jostles particles, occasionally kicking one hard enough to force it out of its delicate superposition and into a single, concrete reality. To visualize this, imagine a very still, calm pond. If you place a ping-pong ball on its surface, it can float in one spot, representing a single, definite state. Now imagine trying to balance a second ping-pong ball directly on top of the first. This precarious tower represents a quantum superposition, two states existing in the same place. In a perfectly calm, isolated environment, this superposition might be stable. But if you begin to agitate the water, creating tiny ripples and waves, the tower will inevitably topple. The top ball will fall to one side or the other, settling into a single, stable location. In this analogy, the agitated water is the quantum foam. Its constant, random fluctuations provide the environmental friction that constantly probes quantum systems, making it increasingly improbable for large, complex superpositions to survive. The foam doesn't care if a conscious observer is present. It is an objective feature of reality that continuously nudges the quantum world toward definite outcomes. This perspective offers a radical solution to the paradox of Schrödinger's cat. In the GRW model, the cat is never truly both alive and dead. The radioactive atom in the box, the Geiger counter, the hammer, and the vial of poison together form a massive collection of particles. The churning background of the quantum foam ensures that within microseconds, one of the trillions of particles in this system will experience a spontaneous collapse, forcing the entire apparatus to choose a path. The superposition of decayed atom and non-decayed atom is destroyed by the objective physical process of foam-induced collapse long before a human ever opens the box. The cat's fate is sealed not by our observation, but by the inherent restlessness of the vacuum itself. The foam acts as a universal quantum referee, constantly enforcing the rules that prevent the blurry quantum world from leaking too conspicuously into our sharp classical reality. Another fascinating angle connects this process to gravity. The Diosy-Penrose model suggests that it is gravity itself, or more precisely, the way gravity couples to a mass distribution that causes the wave function to collapse. In a superposition, an object exists in two slightly different locations at once. According to general relativity, each location corresponds to a slightly different curvature of spacetime. Roger Penrose argues that sustaining these two different spacetime geometries simultaneously is inherently unstable. The universe, in a sense, finds this schizophrenic state of geometry unbearable and quickly resolves the tension by forcing the object to settle into one location or the other. And what is the fundamental fabric of spacetime? It is the quantum foam. The instability could manifest as an increasing turbulence in the foam in the region of the superposition, a kind of geometric stress that can only be relieved by the collapse into a single, consistent geometry. In this view, the transition from quantum to classical is not about size or complexity per se, but about the gravitational influence of a system. The more massive an object is, the more it warps space-time, and the more quickly the foam will conspire to collapse its wave function. This provides a beautifully intuitive explanation for why we never see planets, cats, or people in quantum superpositions. It's not that the laws of quantum mechanics stop applying to large things. It's that their mass creates such a significant gravitational field that the underlying quantum foam cannot support the conflicting geometries for any measurable length of time. The superposition simply self-destructs under its own gravitational weight, orchestrated by the foam's need for a single, consistent reality. The foam, therefore, is not just a passive substrate, but an active participant in shaping reality, acting as a mediator between the smooth, deterministic world of gravity and the probabilistic, fuzzy world of the quantum. It ensures that the stage of spacetime remains solid enough for the actors, you, me, and the entire macroscopic world, to play our parts without the stage itself dissolving into a multitude of conflicting possibilities. But what if the frenetic energy of the quantum foam did more than just fill the vacuum? What if it was the very spark that ignited the formation of everything we see in the cosmos? This idea connects the most microscopic chaos to the grandest cosmic narrative, the theory of inflation. According to this well-supported model, in the first fleeting fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion, blowing up from a subatomic speck to a volume far larger than our entire observable universe. This process was driven by a hypothetical field called the inflaton field, which permeated all of space and possessed a peculiar property. Its energy caused spacetime to repel itself, leading to this incredible burst of growth. For inflation to end and for the universe we know to begin, this field had to decay, releasing its pent-up energy as a fireball of particles and radiation. But there's a crucial piece to this story, and it's where the quantum foam enters in a spectacular way. The inflaton field wasn't sitting in a perfectly smooth, uniform state. Like every other quantum field, it was subject to the inherent uncertainty and randomness mandated by the quantum foam. At every single point in that rapidly stretching spacetime, the value of the inflattened field was jittering, fluctuating up and down due to the same kind of probabilistic frothing that creates virtual particles. Now, here is the truly transformative part of the story. As the universe inflated at a staggering rate, these tiny, random quantum fluctuations in the inflattened field did not get left behind. They were caught in the cosmic expansion and stretched to enormous sizes. Imagine you have a perfectly smooth, stretched rubber sheet, and you flick it with your finger, creating a tiny, localized ripple. Now, imagine that sheet suddenly expands to the size of a continent. That tiny ripple is now stretched into a vast, continent-sized hill and valley. This is precisely what happened during inflation. The microscopic quantum jitters in the inflattened field, ripples that were smaller than a proton one moment, were inflated in a flash to become macroscopic variations in the density of energy across the cosmos. Where the inflattened field had a slightly higher value, the inflation process took a tiny bit longer to end. Where it was slightly lower, it ended a bit sooner. This minute difference in timing, imprinted across the entire sky, resulted in some regions of the universe having ever so slightly more mass and energy than others. These regions of overdensity and underdensity became the cosmic seeds, the blueprint for all future structure. The evidence for this incredible sequence of events is written across the sky in the oldest light we can see, the cosmic microwave background radiation. This is the remnant glow from the moment the universe became cool and transparent enough for light to travel freely, about 380,000 years after the Big Bang. When we map this radiation with satellites like Planck and WMRP, we don't see a perfectly uniform glow. Instead, we see a tapestry of tiny temperature variations, tiny spots that are a few millionths of a degree warmer or colder than the average. These temperature differences are a direct photograph of those primordial density fluctuations. The slightly denser regions appear as slightly cooler spots because the light escaping from them had to climb out of a slightly deeper gravitational well, losing a tiny bit of energy in a process called gravitational redshift. These minute imperfections are the fossilized imprint of the quantum foam, magnified from the subatomic to the cosmic scale. Every galaxy cluster, every supercluster, and the vast cosmic web of filaments and voids that structure our universe today grew gravitationally from these initial ripples. The grand architecture of the cosmos, from the largest scales down to individual galaxies, finds its ultimate origin in the random, probabilistic churning of spacetime at the Planck scale. This provides a profound answer to one of cosmology's oldest questions. Why is the universe so uniform on large scales, yet filled with complex structure? Inflation explains the large-scale uniformity because the entire observable universe came from a tiny, pre-inflationary patch that had time to smooth itself out. And the quantum foam explains the structure. The randomness of the foam provided the necessary imperfections, the initial bumps and wiggles that gravity could then amplify over billions of years. Without the quantum foam's inherent randomness, the inflattened field would have been perfectly smooth. Inflation would have ended uniformly everywhere, and the universe would be a vast, featureless sea of particles, a profoundly boring and lifeless place with no stars, no planets, and no us. The fact that we see a structured universe is a direct testament to the active, unpredictable nature of the quantum vacuum in the first instance of time. The foam provided the creative noise, and inflation provided the amplifier, working in concert to transform quantum uncertainty into the cosmic structures that define our reality. Yet for all the universe's intricate structure, a ghost haunts the foundations of modern physics, a numerical nightmare that remains arguably the greatest unsolved problem in fundamental science. We've encountered it before, the vacuum catastrophe, where our best calculation of the vacuum energy generated by the quantum foam overshoots the observed value of dark energy by a factor of 1 followed by 120 zeros. It's a failure so spectacular it's like predicting that a single breath should generate the force of 1 trillion hydrogen bombs, while in reality it barely stirs a feather. But physicists are not ones to surrender easily, and the quest to resolve this catastrophe has led to some of the most profound, and in some cases philosophically unsettling, proposals ever conceived. Let's revisit this abyss and peer into the exotic solutions that attempt to bridge this unimaginable gap. One of the most discussed and debated avenues is the anthropic principle. This is not a mechanistic solution in the traditional sense, but a fundamental shift in perspective. It begins with the concept of the multiverse. If our cosmos is just one bubble in a vast, perhaps infinite, foam of universes, each with different randomly selected physical constants, then the value of the cosmological constant could be different in each one. In the overwhelming majority of these universes, the vacuum energy would be immense. If it were positive and large, space would have ripped itself apart in the first instant, preventing any structure from ever forming. If it were negative and large, the universe would have collapsed back into a big crunch almost immediately. We quite obviously find ourselves in one of the exceptionally rare Goldilocks-style universes where the cosmological constant is minuscule, not because of a beautiful underlying symmetry, but simply because such a universe is the only kind that can support the long, slow evolution of galaxies, stars, planets, and ultimately, life forms capable of asking why the number is so small. From this vantage point, the vacuum catastrophe isn't a problem to be solved by a single equation. It is a selection effect. We are here because the number is small, not the other way around. While this can feel like a cop-out to those seeking a deterministic first principles answer, it forces a profound philosophical reckoning. It suggests that some of the most basic features of our reality, features we long assumed were dictated by immutable, elegant laws, might instead be environmental accidents, local byproducts of our specific cosmic address. The quantum foam's ferocious energy isn't tamed by a clever mathematical trick. We just happen to live in a bubble where, by sheer random chance, it almost perfectly cancels out. This doesn't make the foam any less real, but it does potentially relocate the ultimate explanation for our existence from the realm of pure mathematics to the realm of statistics and probability in a cosmos of infinite variety. A more traditional, and for many more satisfying, approach seeks a physical mechanism for that near-perfect cancellation. This line of thinking asks if there is a hidden symmetry or a dynamic adjustment process that forces the net vacuum energy to be zero or very nearly so. One of the most elegant candidates is supersymmetry. This theory posits that for every known fundamental particle, every electron, every quark, there exists a superpartner, a shadow particle with subtly different properties. If this symmetry were unbroken, meaning these superpartners had the same mass as their ordinary counterparts, their contributions to the quantum foam would be perfectly mirrored. For every virtual particle fluctuation that contributes a positive energy to the vacuum, its superpartner would contribute an equal and opposite negative energy. The sum total would be exactly zero, resolving the catastrophe with breathtaking neatness. The problem, of course, is that we don't see these superpartners. This means supersymmetry, if it exists, must be a broken symmetry, with the superpartners being far too heavy for our current particle colliders to detect. In this broken state, the cancellation is very good, potentially reducing the discrepancy by dozens of orders of magnitude, but it is not perfect. The hunt for any sign of these particles remains one of the most intense endeavors in physics, as their discovery would provide a colossal step toward taming the vacuum's wild energy. Another fascinating, though highly speculative, idea involves the dynamics of the foam itself. What if the frantic creation and annihilation of virtual particles isn't the full story? Some theories suggest that the structure of spacetime at the Planck scale might be far more complex, with the foam consisting not just of particle-antiparticle pairs, but also of gravitational instabilities that contribute negative energy. John Wheeler's vision included a seething soup of virtual black holes and wormholes. These gravitational entities, governed by the peculiar rules of general relativity where gravity can act repulsively, could contribute a negative energy density to the vacuum. The tantalizing possibility is that the positive energy from matter and force fields is almost exactly balanced by the negative energy from these gravitational fluctuations. The universe, in a sense, could be taking out a vast loan of positive energy for particle creation, but securing it with an equally vast gravitational lien of negative energy, resulting in a net balance sheet that is very close to zero. The tiny residue we measure as dark energy could then be the faint leftover imbalance from this cosmic accounting, a residual 1 part in a trillion effect that is only noticeable on the very largest scales. This leads to an even more radical notion. What if the cosmological constant isn't a constant at all? The idea of a dynamic vacuum energy, sometimes called quintessence, proposes that the energy density of the void has changed over the life of the universe. In the early cosmos, it might have been the driving force behind inflation, and has since decayed to the very low value we see today. In this scenario, the catastrophic calculation we perform today, which assumes a static vacuum, is misleading. The quantum foam's effective energy output could be governed by a field that is still slowly evolving, seeking its true minimum. We might be living at a special time in cosmic history where the value is small enough for life to exist but not zero. The problem then transforms from why is it so small to why is it in this particular slow-rolling phase now? While this doesn't solve the fundamental issue, it opens up new avenues for exploration, suggesting that the vacuum catastrophe might not be a static puzzle, but a dynamic one, with an answer that is written in the evolving history of the cosmos itself. Ultimately, the vacuum catastrophe stands as a monumental signpost pointing directly to the limits of our current knowledge. It is a stark reminder that merging quantum field theory with gravity is not just a technical exercise, but a conceptual revolution waiting to happen. The solutions, whether they lie in a multiverse landscape, a broken supersymmetry, a self-canceling foam, or a dynamic field, all require physics beyond our current established models. The very fact that empty space has any energy at all, and that this energy is so inexplicably faint, may be the most important clue we have in our quest for a final theory. It tells us that the quietest thing we can possibly measure, the hum of nothingness, is in fact screaming the secrets of quantum gravity, if only we can learn to listen. One of the most elegant and long-standing proposals to tame the vacuum's ferocious energy arrives in the form of a beautiful symmetry, a mathematical harmony that would fundamentally double the population of the universe's elementary particles. This is the principle of supersymmetry, often abbreviated as SUSY. It postulates a profound and resonant partnership in the very bedrock of reality. For every known fundamental particle that makes up matter and carries forces, there exists a superpartner, a kind of shadow twin. For every quark, there would be a squark. For every electron, a selectron. The photon, the particle of light, would be paired with the photino, and the list continues throughout the entire standard model of particle physics. This isn't just a whimsical doubling for the sake of complexity. It's a potential key to locking the unruly quantum foam into a state of serene balance. The magic of supersymmetry lies in the specific properties of these superpartners. While an electron is a fermion, a type of particle that constitutes matter, its superpartner, the selectron, would be a boson, a type of particle that carries force. This distinction is absolutely critical because these two families of particles contribute to the energy of the vacuum in fundamentally opposite ways. The frenetic dance of virtual fermions in the quantum foam tends to push the vacuum energy in a negative direction. In contrast, the fluctuations of virtual bosons drive it in a positive direction. In our current, non-supersymmetric universe, these contributions are wildly out of sync, leading to that catastrophic positive sum. But if supersymmetry were an exact, unbroken symmetry of nature, meaning every particle and its superpartner had identical mass, their contributions would be perfectly mirrored. The negative energy from the virtual fermions and the positive energy from the virtual bosons would cancel each other out with exquisite precision, driving the net cosmological constant to exactly zero. The quantum foam would still be churning, but its net energy output would be perfectly balanced, as if the universe's most chaotic storm was somehow producing perfectly calm seas. This elegant cancellation would do more than just solve the vacuum energy problem. It would also address another monumental puzzle known as the hierarchy problem. This conundrum asks why the force of gravity is so unimaginably weaker than the other fundamental forces. The electromagnetic force, for instance, is a trillion times stronger than gravity. This is a disparity so vast it seems to demand an explanation. In the quantum foam, the Higgs boson, the particle that gives others mass, is constantly buffeted by these ultra-high-energy fluctuations. These interactions should drive the Higgs's mass, and by extension the masses of all particles up to the Planck scale, making our familiar world of atoms and molecules impossible. Supersymmetry acts as a protective shield. For every virtual particle fluctuation that tries to push the Higgs mass to an enormous value, its superpartner fluctuation provides an equal and opposite pull, stabilizing the mass at the much lower, observed energy scale we see in our world. In this picture, the delicate structure of our reality, with its specific particle masses and forces, isn't a precarious accident. It's actively maintained by the balancing act of supersymmetry, which uses the foam's own chaotic energy against itself to preserve a stable, life-friendly universe. The foam is stabilized, and with it the entire energetic hierarchy of the cosmos. However, there is a very significant and obvious catch. If every particle had a superpartner with the same mass, we would have discovered them long ago. A selectron would have the same mass as an electron and would be just as easy to produce and detect in our particle colliders. We don't see this. There is no selectron, no squark. This means that if supersymmetry is a real property of our universe, it must be a broken symmetry. The superpartners are not missing. They are just much heavier than their ordinary counterparts. In the earliest, hottest moments of the Big Bang, this symmetry would have been perfect and unbroken. Particles and their superpartners would have been indistinguishable, and the vacuum energy would have been perfectly cancelled. But as the universe cooled and underwent a phase transition, supersymmetry broke. The superpartners acquired enormous masses, pushing them far beyond the energy levels we can currently probe. In this broken state, the beautiful cancellation is no longer perfect. The contributions to the vacuum energy no longer sum to zero, but the residual value could still be dramatically smaller than the uncancelled disaster predicted by the standard model. Supersymmetry could reduce the discrepancy from 120 orders of magnitude to a far more manageable, though still puzzling, few dozen. It gets us part of the way there, taming the foam's most violent tendencies even if it doesn't entirely pacify it. The ongoing, decades-long search for these superpartners is one of the great quests in modern physics. Powerful particle colliders like the Large Hadron Collider have been meticulously scouring higher and higher energy ranges, listening for the faint signature of a squark or a gluino being created in a collision. So far, the silence has been profound. This non-detection is itself a meaningful result, forcing theorists to refine their models and consider that supersymmetry, if it exists, might be realized in a way that places the superpartners at energies even higher than initially hoped. Some physicists remain deeply optimistic, believing we are on the cusp of discovery at the next energy frontier. Others are growing skeptical, wondering if nature might have chosen a different, even more clever path to stability. Yet the profound mathematical beauty and explanatory power of supersymmetry keep it as a leading candidate. It represents a vision of the quantum foam not as a formless chaos, but as a deeply structured and balanced system, where every violent fluctuation is inherently paired with a calming, counterbalancing influence. Even in its broken form, it suggests a universe that strives for harmony, using the mechanism of supersymmetry to build a stable, structured world from the frothing potential of the vacuum. What if the smooth, continuous stage of spacetime we take for granted is not the final layer of reality, but merely a sophisticated facade? This brings us to a frontier of theoretical physics that dares to ask, what lies beneath geometry itself? The concept of progeometry proposes exactly that. The familiar four-dimensional continuum of space and time is not fundamental. Instead, it emerges from a deeper, more primitive layer of reality composed of entities that are not themselves spatiotemporal. These are the true atoms of existence, the ultimate building blocks whose collective dance and complex relationships give rise to the quantum foam. And from that foam, the illusion of a seamless cosmos crystallizes. Imagine trying to explain the concept of a wave to someone who has only ever encountered individual water molecules. A single molecule has no wavelength, no frequency, no crest or trough. These are collective properties, emergent phenomena that only manifest when trillions of molecules interact in a specific, coordinated way. Progeometry suggests that spacetime and its geometry are the cosmic equivalent of that wave. The individual water molecules are the progeometric atoms, the true fundamentals that possess none of the geometric properties they ultimately create. So, what could these non-spatiotemporal atoms possibly be? The proposals are as abstract as they are fascinating. They are not tiny bits of matter or energy floating in a void, because the void itself, space, is what they conspire to produce. Some theories suggest they are pure bits of information, like the ones and zeros in a cosmic computer, whose patterns of connection define reality. Others propose they are simple mathematical relationships or logical operations. In loop quantum gravity, for instance, we encountered the spin network, a web of discrete quanta of space. Progeometry takes a step further back, asking what the nodes and links of that network are made of before they even represent volumes and areas. They might be abstract elements whose only properties are how they relate to one another. Think of the members of a vast cosmic social network. No single person is the concept of community, but their collective friendships, enmities, and communications give rise to the emergent structure of the society itself. In the same way, progeometric atoms have no inherent location or extension. Their identity is defined entirely by their relationships, and from this web of pure connection, the geometry of space somehow materializes. How does this sea of abstract relationships transform into the churning quantum foam? The foam in this picture is the intermediate stage, the turbulent interface between the placeless, timeless world of progeometry and our own structured reality. The frantic bubbling of virtual particles and the flickering of microscopic wormholes are not the fundamental activity. They are the visible symptoms of a much deeper process. They are the result of the progeometric atoms constantly updating their relationships, a dynamic and probabilistic computation happening at the absolute bottom level of reality. Each fluctuation in the foam corresponds to a shift in the underlying network of connections. A virtual particle pair flashing into existence might be the consequence of a fundamental logical operation between two progeometric bits. A wormhole might be a temporary, direct connection formed between two distant parts of the network, a shortcut that momentarily redefines what distant even means. The foam is the dynamic, probabilistic texture of this emerging geometry, the cosmic static we perceive when we look closely at the process of reality rendering itself into being. One of the most compelling motivations for progeometry is its potential to resolve the deepest paradox of quantum gravity, the problem of background dependence. In Einstein's general relativity, gravity is the geometry of spacetime. The theory needs this geometric stage to exist in order to describe how it curves. But when we try to quantize gravity, this creates a circular problem. We're trying to apply quantum rules to the very thing that defines the stage for those rules. It's like trying to explain the rules of a game while simultaneously defining the board on which it's played. Pre-geometry cuts this Gordian knot by eliminating the stage altogether. There is no pre-existing spacetime. The pre-geometric atoms and their interactions are the entire show. Spacetime, along with its gravitational field, condenses out of this more primitive substrate, much like the concept of temperature emerges from the frantic motion of atoms that individually have no temperature. This means that at the most fundamental level, there is no conflict between gravity and quantum mechanics because there is no geometry for them to conflict over. They both emerge hand in hand from the same pre-geometric foundation. To visualize this abstract concept, consider the world of computer graphics. A beautifully rendered, three-dimensional landscape in a video game seems to have mountains, valleys, and a vast open sky. But at the fundamental level of the computer's hardware, none of that exists. There are only transistors, billions of them switching on and off according to the rules of Boolean logic. There is no space inside the processor, only electrical currents and voltage states. The three-dimensional world is a higher-level interpretation, an emergent illusion generated by the complex, structured relationships between those on-off states. The game's physics engine, which simulates gravity and collisions, is not a fundamental force running on the hardware. It is a high-level algorithm that emerges from the lower-level code. In the pre-geometric universe, the transistors are the pre-geometric atoms. The laws of physics, including gravity and quantum mechanics, are the stable, high-level algorithms that run on this cosmic hardware. The quantum foam is the visual noise you might see if you could peer into the processor at the moment it's translating the fundamental code into the grand, cosmic simulation we call reality. This perspective transforms our understanding of the vacuum catastrophe and the nature of existence itself. The monstrously large vacuum energy we calculate might be a classic error of category. We are trying to calculate the energy of fluctuations within spacetime, but if spacetime is not fundamental, this calculation is meaningless. It's like trying to calculate the weight of a character in a video game by weighing the computer's hard drive. The energy of the quantum foam may not be a physical energy in the traditional sense, but rather a measure of the computational cost or the complexity of the relationships within the pre-geometric network. The tiny residual value we observe as dark energy could then be a kind of baseline activity level of the cosmic processor, the minimal hum required to keep the simulation of reality running. In this grand vision, pre-geometry does not just explain the foam, it recontextualizes it, suggesting that the universe's deepest foundation is not a place of chaotic energy, but a realm of pure dynamic relation, a silent foundational logic whose output is the spectacular, foamy, and glorious illusion of everything that is. This exploration into the quantum foam has taken us from the birth of universes to the preservation of information. But now we encounter a paradox so fierce it seems to set the very laws of physics against each other. This is the black hole firewall paradox, a thought experiment that emerged in the early 2012, and it presents an excruciating choice for theoretical physicists. The problem begins with a seemingly simple question: what would happen to an astronaut falling into a large, old black hole? According to Einstein's principle of equivalence, the cornerstone of general relativity, the experience should be entirely uneventful, at least initially. Since the black hole's gravity is the curvature of spacetime itself, an astronaut in freefall should feel no forces at all as they cross the event horizon. They would be seamlessly absorbed into the black hole's interior, a process often called spaghettification, only occurring much later as they approach the central singularity. For the astronaut, the horizon is not a brick wall. It is a silent, invisible threshold they pass without even noticing. However, quantum mechanics tells a completely different and terrifying story. To understand why, we must revisit the process of Hawking radiation and the fate of information. As we've discussed, black holes slowly evaporate by emitting radiation, and quantum mechanics demands that this radiation must, in principle, carry out the information about everything that fell inside. To preserve this information, the outgoing Hawking radiation must be subtly entangled with the radiation that left earlier in the evaporation process. This is a fundamental requirement of quantum mechanics to maintain a consistent history of the universe. But here is the devastating catch. For the information to be successfully encoded in the radiation, the outgoing Hawking particle must also be entangled with its partner, the particle that fell into the black hole. This creates a quantum love triangle, an impossible situation. The infalling particle is deeply entangled with its partner inside the black hole, but for information to escape, the outgoing particle must also be entangled with that same infalling partner. Quantum mechanics has a strict rule known as the monogamy of entanglement. A single quantum particle cannot be fully entangled with two different systems at the same time. One of these entanglements must be broken. The firewall paradox is the brutal resolution to this impasse. It suggests that the entanglement between the infalling particle and its partner inside the black hole is violently severed right at the event horizon. In the language of quantum field theory, this sudden, forceful disconnection releases an immense amount of energy. The consequence is that the event horizon is not a quiet place of freefall, but a blazing wall of fire, a firewall of incalculable energy that would instantly incinerate any astronaut or particle attempting to cross it. This resolves the quantum inconsistency by burning up the infalling information, but it does so by utterly demolishing the smooth spacetime of general relativity. We are left with a stark either-or choice. Either we abandon the principle of equivalence and the smoothness of spacetime, accepting that black holes are surrounded by a lethal firewall, or we admit that quantum information is somehow lost, violating a core tenet of quantum theory. Both options are deeply unpalatable, pointing to a fundamental flaw in our understanding. So, where does the quantum foam fit into this infernal dilemma? The resolution may lie in a radical reimagining of its structure precisely at the event horizon. The standard picture of the vacuum, even a foamy one, assumes a certain level of smoothness and locality on average. The firewall argument relies on this assumption. But what if, at the horizon of a black hole, the quantum foam undergoes a dramatic phase transition? It might reorganize itself into a state of such extreme chaos and non-locality that our conventional concepts of entanglement and particle states simply break down. In this view, the event horizon is not a sharp, two-dimensional surface, but an incredibly thick, turbulent shell of spacetime foam. An astronaut approaching it wouldn't encounter a sudden wall of fire, but would instead experience a gradual and profound dissolution of their own reality. As they enter this foamy boundary layer, the very distinction between inside and outside the black hole becomes blurred. The neat, separable quantum states that lead to the firewall paradox may not even be definable in such a frothy, non-local environment. This idea connects powerfully to the fuzzball proposal from string theory that we touched on earlier. A fuzzball black hole has no smooth interior and no sharp event horizon. Instead, it is a giant, tangled ball of strings and energy that extends right out to where the horizon was supposed to be. In this picture, an astronaut would never experience freefall through a horizon because there is no other side to fall into. Instead, they would simply collide with the complex, stringy structure of the fuzzball itself and be immediately assimilated, their information scrambled throughout the entire object. The firewall is replaced by a fuzzball wall, but one that is not made of energy in the conventional sense. It is a wall of quantum complexity, a region where the fabric of spacetime is so thoroughly chewed up by the foam that the very question of what happens to an individual particle loses its meaning. The information isn't burned, it is instantly delocalized and stored in the intricate web of the fuzzball structure, from which it can later be released in the Hawking radiation without violating any quantum rules. This suggests that the firewall is less a physical object and more a signal that we are applying the wrong conceptual framework. We are trying to describe a process at the black hole boundary using ideas from quantum field theory that assume a calm, flat spacetime background. But the quantum foam at the horizon is anything but calm. Its structure is so wildly fluctuating and interconnected that the notion of a localized particle with well-defined entanglements becomes invalid. The paradox arises because we are forcing this smooth, particle-based description onto a regime where it doesn't apply. The true resolution may be that the foam's architecture at the horizon is so alien that it transcends the either-or choice presented by the firewall. It allows for a third option where information is preserved without a lethal firewall, but only by demanding that we let go of our classical intuition about the nature of surfaces and boundaries entirely. The event horizon is not a line in the sand. It is a stormy, quantum mechanical shore where the waves of reality crash and merge in ways we are only beginning to fathom. What if the universe's very geometry wasn't a given, but something that literally froze into place, like the crystal structure of ice forming in supercooled water? This is the startling vision of quantum gravity, a theory that proposes spacetime itself underwent a dramatic phase transition in its infancy, emerging from a primordial state of pure connection that knew nothing of distance or dimension. Picture the earliest moments of reality not as a hot, dense point, but as a brilliant, abstract web, a graph of an almost unimaginable kind. In this initial state, every single point of this nascent universe was directly connected to every other point. There was no far away because everything was a neighbor, linked in a single, vibrant network of instantaneous relation. This is known as a complete graph, a state of maximum connectivity and minimum geometry, where the concept of space as we know it simply did not yet exist. It was a cosmos of pure potential relationship, a buzzing, energetic hive where every location was just one step from any other. Then, as the universe expanded and cooled, something remarkable happened, analogous to water freezing. The highly connected, high-energy graph could no longer sustain its frantic state. The system underwent a spontaneous symmetry breaking, a cosmic freezing. Just as water molecules settle into a rigid, crystalline lattice of ice, the links in this cosmic graph began to snap. The vast majority of the primordial connections broke, and in doing so, they defined a new reality. The points that remained directly connected became what we now perceive as points that are close together in space. The points that lost their direct links became separated by vast distances. The pattern of broken and preserved connections literally crystallized to form the geometry of three-dimensional space. The void between stars isn't truly empty. It is etched with the memory of links that were severed in the early cosmic freeze, defining the vast separations we now measure in light years. So, where does the quantum foam fit into this graph-theoretic picture? The foam is the residual energy, the leftover jitters and vibrations of this frozen graph. Even in a solid piece of ice, atoms continue to vibrate. In the frozen graph of space-time, these vibrations are the fundamental excitations. Think of the graph not as a static, rigid crystal, but as a dynamic, elastic fabric. The low-energy ripples and oscillations propagating through this network of connections are what we detect as the virtual particles and fluctuations of the quantum foam. A virtual electron-positron pair blinking into existence might correspond to a temporary, localized vibration in the graph, a fleeting distortion of the connections between nodes. A microscopic wormhole could be a momentary reconnection, a brief re-establishment of a primordial link that was frozen out long ago. In this model, the foam is not a separate substance. It is the natural thermal vibration of spacetime's own atomic lattice, a lattice built not from points in space, but from the very relationships that define space itself. This perspective offers a breathtakingly elegant solution to the problem of unifying general relativity with quantum mechanics. In quantum gravity isn't a force that warps a pre-existing stage. Gravity is the dynamics of the graph. The curvature of spacetime described by Einstein is an emergent property of how the connectivity of the graph varies from place to place. A region of high connectivity might correspond to a region of intense gravity, like near a black hole, while a region of low, uniform connectivity describes the flat, empty space between galaxies. The quantum foam, then, represents the granular quantum mechanical nature of this underlying graph. The famous non-commutative geometry we discussed earlier finds a natural home here. The inherent fuzziness of location arises because the fundamental reality is this network of relations, not a set of points. You cannot pinpoint a location with infinite precision because the points are defined by their connections, which are themselves dynamical and subject to quantum uncertainty. To make this abstract idea more tangible, imagine a vast social network like the entire population of the world. In its initial state, every person is directly friends with every other person. This is the hot, high-energy, completely connected graph. Then, as the system evolves and cools, people can only maintain a limited number of close friendships. Most of the global connections are lost. The pattern of who remains connected to whom defines the social geometry. Clusters of tightly knit friends become local neighborhoods, while the loss of a direct connection between two people on opposite sides of the planet defines a vast social distance. Now imagine the constant, low-level buzz of communication within this network. A text message here, a phone call there. This ongoing communication is the analog of the quantum foam. It's not the structure of the network itself, but the dynamic activity happening upon it. And this activity is what gives the network its lively, unpredictable character. The universe, in the quantum gravity model, is this cosmic social network, with the quantum foam being the endless, silent conversation that continuously plays out across its frozen, geometric connections. This brings us to a theory that stands apart from all the others, for it places the mystery of the quantum foam in direct conversation with the most profound mystery we know from the inside, the nature of our own consciousness. We have explored how the foam might collapse due to gravity or spontaneously or through environmental noise. But what if the ultimate catalyst for reality's crystallization is something far more intimate, the very act of conscious observation itself? This is not the standard interpretation of quantum mechanics, but a far more radical and speculative proposal, one most famously championed by the Nobel laureate Roger Penrose. He, along with anesthesiologist Stuart Hameroff, has put forward a theory known as orchestrated objective reduction, or ORCH, which daringly suggests that consciousness is not an emergent property of complex computation in the brain, but a fundamental feature of the universe, deeply rooted in the quantum geometry of spacetime, and it plays an active role in taming the probabilistic foam. The definite world we perceive. To understand this, we must first grasp Penrose's unique take on the measurement problem. He was deeply dissatisfied with the idea that the wave function collapses due to the vague concept of measurement. What is so special about a measuring device? Isn't it itself made of quantum particles? Penrose proposed that the collapse is an objective physical process, but one triggered by a very specific instability, gravity. His reasoning is beautifully geometric. Imagine a single particle in a quantum superposition, existing in two slightly different locations at once. According to general relativity, each location corresponds to a slightly different curvature, a different bending of spacetime. For a single particle, the difference in spacetime geometry between the two states is negligible. But now, consider a massive object like a cat or a human brain in a superposition. The two possible states would describe two significantly different spacetime geometries. Penrose argues that the universe finds this schizophrenic state of its own fabric fundamentally unstable. It is a kind of blister on reality, a tension in the very foundation of things that cannot be sustained. This gravitational instability, he proposes, causes the superposition to spontaneously and objectively reduce or collapse into one reality or the other. The catalyst isn't a conscious observer in the abstract, but the objective gravitational weight of the situation itself. So, where does consciousness enter this gravitational picture? This is where the theory ventures into its most fascinating and controversial territory. Penrose and Hamroff suggest that the microscopic structures within our brain's neurons, specifically proteins called microtubules, are the perfect candidates to harness this objective reduction. Microtubules are tiny, cylindrical scaffolds that form the cytoskeleton of cells, and in neurons, they are incredibly abundant and organized. Orch proposes that these microtubules are engineered to isolate and protect quantum superpositions. Within their shielded, ordered interiors, electrons could become superposed, existing in multiple states simultaneously. This superposition would create the tiny, conflicting spacetime geometries Penrose described. As this gravitational instability builds, it reaches a threshold, and the superposition collapses not randomly, but in a way that is orchestrated by the biological structure of the microtubules. It is this specific, non-computable wave function collapse event that, according to the theory, gives rise to a single, discrete moment of conscious experience. In this view, our stream of consciousness is not a continuous flow, but a sequence of these rapid, quantum collapses happening perhaps 40 times per second, each one a flicker of awareness born from the resolution of a tiny knot in the quantum foam within our own heads. This leads to a breathtaking implication for the nature of reality. If consciousness arises from the objective collapse of the wave function, then it is not a passive spectator. It is an active participant in the cosmic process of making things real. Every conscious observation is a moment where the frothing sea of quantum possibilities is calmed, where a specific thread of reality is chosen from the tapestry of the foam. Our awareness is not just watching the universe, it is in a constant, subtle dialogue with its most fundamental layer, helping to stitch the probabilistic quantum world into the definite classical world we navigate. The quantum foam, then, is not just out there in the vacuum of space. It is right here, inside the very fabric of our minds, and our consciousness is the process by which we interact with it, moment by moment, shaping our reality as it shapes us. Of course, this theory is met with significant skepticism within the broader physics community. Critics point out that the warm, wet, and chaotic environment of the brain seems utterly hostile to maintaining the delicate coherence of quantum states, which in laboratories require extreme cold and isolation to protect from environmental decoherence. The idea that such processes could be happening in our biology is for many a bridge too far. Furthermore, pinning down a precise biological mechanism for such a profound phenomenon remains an immense challenge. Yet the power of the Orch proposal lies not in its certainties, but in the profound questions it forces us to confront. It challenges the reductionist view that consciousness is merely an emergent illusion generated by neural complexity, suggesting instead that it may be a fundamental physical process as integral to the cosmos as gravity or spacetime. It dares to draw a connecting line between the inner universe of our subjective experience and the outer universe of quantum mechanics, proposing that the two are not separate realms, but deeply and mysteriously intertwined in the ongoing creation of everything that is. But after so many theories based on pure thought and mathematical elegance, how could we ever hope to find tangible, observational proof for something as ethereal as the quantum foam? This challenge brings us to a groundbreaking frontier where abstract theory meets hard, observational science, using some of the most violent and distant explosions in the cosmos as our laboratory. The idea is surprisingly straightforward, yet its implications are profound. If spacetime is truly a churning, foamy mess at the Planck scale, then it shouldn't be perfectly smooth for light traveling across billions of light years. Think of it like this. Imagine you're trying to run across a perfectly manicured lawn versus a field that's been churned up by a storm, full of tiny ruts and bumps. On the smooth lawn, you can run in a straight line at a constant speed. But on the bumpy field, your path would be slightly jostled, and you might even slow down a tiny bit as your feet navigate the uneven ground. In the same way, physicists propose that the quantum foam's turbulent structure should act like microscopic bumps in the road for photons, the particles of light. A photon's journey wouldn't be perfectly unimpeded. It would experience subtle, stochastic fluctuations in its speed caused by its interaction with the foamy texture of spacetime itself. This is where gamma-ray bursts become our most powerful tool. These are not just any astronomical events. They are the single most energetic explosions known to occur in the universe since the Big Bang itself, often releasing in a few seconds more energy than our Sun will emit in its entire 10 billion-year lifetime. They are thought to be caused by the cataclysmic death of massive stars or the merger of ultra-dense neutron stars, events so powerful they beam intense flashes of high-energy gamma-ray radiation across cosmic distances. For our purposes, they act as the universe's ultimate lighthouse, sending a tremendously bright, short-duration pulse of light from the edge of the observable cosmos. Crucially, this light is not a single wavelength. A gamma-ray burst emits photons across a vast spectrum of energies, from lower-energy gamma rays to immensely high-energy ones. According to the foam-induced jitter, these different energy photons should not all arrive at our telescopes at exactly the same time. The higher-energy photons, with their smaller wavelengths, should be more susceptible to the fine-grained structure of the foam. They would effectively feel the bumps more than their longer wavelength, lower energy counterparts. Over a journey of billions of years, this tiny cumulative effect could cause a noticeable spreading out or dispersion in the arrival times of the burst's photons. The highest energy photons might arrive a fraction of a second later than the lower energy ones, a delay that would be a direct signature of the foam's granularity. To grasp the scale of this experiment, consider the distance involved. The photons from these bursts have been traveling for over 10 billion years through a vacuum that we once thought was perfectly pristine and uniform. If the quantum foam exists every single Planck length of that unimaginable journey, and there are more Planck lengths in a centimeter than there are centimeters across the entire observable universe, represents a potential minuscule interaction. Each interaction might only alter a photon's speed by an amount so small it's beyond human comprehension, but the sheer number of these interactions across such a vast distance could add up to a measurable effect. It's a statistical experiment on a cosmic scale. We are not looking for one big bump. We are looking for the collective whisper of 10 to the power of 100 tiny bumps, a whisper that manifests as a tiny time delay in the most energetic light. So, what have the observations revealed? Teams of astronomers have meticulously analyzed data from powerful telescopes like the Fermi Gamma-Ray Space Telescope and the Magic Atmospheric Cherenkov telescopes, searching for this telltale dispersion in the light curves of distant gamma-ray bursts. The results thus far have been both intriguing and sobering. For the most part, the highest energy photons from these ancient explosions have arrived at Earth in remarkable lockstep with their lower energy siblings. The observed delays are either much smaller than some foam models predicted or are entirely consistent with being zero. This doesn't mean the quantum foam isn't real. Rather, it places severe constraints on its possible nature. The smooth arrival of this light suggests that if spacetime is foamy, its texture must be much finer, or its effects on light much weaker than the most dramatic theories proposed. It rules out certain classes of models, particularly those that predicted a strong energy-dependent delay, forcing theorists back to the drawing board to develop more subtle and sophisticated descriptions of the foam's structure. This incredible endeavor highlights a beautiful symmetry in modern physics. We are using the largest explosions in the universe, events that tear apart stars and forge elements, to probe the very smallest possible structures of reality. The journey of a single photon from a dying star 10 billion light-years away becomes a precision test of the fabric of spacetime itself. The fact that we see such little dispersion is, in its own way, a profound discovery. It tells us that the vacuum of space, for all its supposed quantum chaos, is astonishingly transparent and uniform for light traveling across cosmic epochs. The stage upon which the drama of the cosmos plays out is, on average, incredibly smooth, even if its foundations are a seething, probabilistic storm. The search continues with every new gamma-ray burst that flashes in the distant darkness, each one a new data point in our ongoing quest to understand whether the universe is built upon a foundation of solid geometry or a frenetic, ever-changing quantum foam. Looking forward, the quest to move from mathematical speculation to direct experimental proof of the quantum foam is driving a new generation of technologies so precise they border on the magical. The central challenge is one of scale. The frantic activity of the foam occurs at the Planck length, a distance so infinitesimally small that comparing it to the size of an atom is like comparing that atom to our entire solar system. We will never build a microscope powerful enough to peer directly into this realm. So, how can we possibly test its existence? The answer lies in cleverness over brute force, in designing experiments that amplify the foam's subtle effects or catch its faint echoes across the vastness of space and time. The next great leap in physics will come not from a single revolutionary machine, but from a symphony of different approaches, each listening for the universe's faintest whispers in a different key. One of the most promising terrestrial experiments involves a device that sounds like science fiction, the atomic interferometer. Imagine taking a single atom and using laser pulses to put it into a quantum superposition, effectively splitting it into two paths that travel separately before being recombined. In a perfectly smooth, classical spacetime, the two paths would interfere with each other in a predictable, precise pattern when they meet. But if spacetime is truly foamy at a fundamental level, that foamy texture should introduce a subtle, stochastic jitter into the experiment. It would be like trying to measure the perfect calm of a pond's surface while invisible, microscopic creatures are constantly disturbing the water. The quantum foam would act as a form of intrinsic noise, causing tiny, random shifts in the phase of the interfering atoms. By comparing the interference patterns of two nearby interferometers, or by running one experiment for an extended period, physicists hope to detect this fundamental noise floor of the universe. If they can isolate it from all other sources of vibration and thermal noise, the remaining jitter could be the first direct signature of the spacetime foam churning beneath our feet. These experiments are becoming so sensitive that they are now probing scales only a few orders of magnitude away from the Planck length, bringing us closer than ever to touching the grain of reality itself. Meanwhile, high above the Earth, another window is opening through the revolutionary field of gravitational wave astronomy. The LIGO and Virgo observatories have already given us ears to hear the cosmic collisions of black holes and neutron stars, events that shake the very fabric of spacetime. The next step is to listen for a far more subtle chorus, the gravitational wave background from the very early universe. In the first fleeting instance after the Big Bang, when the quantum foam was the dominant feature of reality, the universe should have been a cacophony of primordial gravitational waves generated by the foamy, quantum gravitational fluctuations of spacetime itself. Detecting this background would be like hearing the residual echo of the creation event. Future space-based observatories like the proposed Laser Interferometer Space Antenna, or LISA, are designed specifically for this purpose. By placing 3 spacecraft millions of kilometers apart in a precise triangular formation, LISA will create a gravitational wave observatory of staggering size and sensitivity, capable of detecting the low-frequency hum of these ancient ripples. Finding this signal would not only confirm the violent quantum gravitational nature of the early universe, but could also allow us to distinguish between different models of the foam, as each theory predicts a slightly different pattern in the gravitational wave spectrum. On the energy frontier, the world's most powerful particle colliders also have a role to play, albeit indirectly. While they cannot reach the Planck energy directly, that would require an accelerator larger than our galaxy. They are hunting for the shadows of new physics. The primary target remains supersymmetry. As we discussed, supersymmetry is a compelling candidate for taming the quantum foam's violent energy and stabilizing the Higgs field. The continued search for superpartner particles at facilities like the Large Hadron Collider and its planned successors is a crucial test. Finding even a single superpartner would provide monumental indirect evidence that the universe possesses the kind of deep symmetry needed to control the foam's chaos. Furthermore, by meticulously studying the behavior of the Higgs boson and other known particles, physicists can probe for tiny deviations from the predictions of the Standard Model. These minuscule anomalies could be the fingerprints of the hidden, foamy structure of spacetime, subtly influencing particle interactions at high energies. It's a painstaking process of exclusion and precision, where every measurement that aligns perfectly with the old models pushes us to imagine new, more exotic possibilities for the foam's true nature. Perhaps the most profound test of all will come from observing the absolute oldest light in the cosmos. We've already seen how the pattern of the cosmic microwave background radiation is a fossilized imprint of quantum fluctuations stretched to cosmic size. Future observatories, such as the CMB-S4 project, aim to map this radiation with unprecedented resolution. They will be looking for a specific telltale signature known as primordial gravitational waves imprinted as a unique pattern of polarization, often called B modes in the CMB light. This pattern is a direct prediction of cosmic inflation, the theory that itself is powered by quantum field fluctuations. Detecting it would strongly reinforce the entire paradigm that the large-scale structure of our universe was seeded by quantum jitters. But even more daringly, by analyzing the statistical properties of these fluctuations in excruciating detail, cosmologists hope to find clues about the pre-geometric phase that preceded inflation. The specific statistical distribution of the hot and cold spots on the CMB sky could, in theory, reveal whether the initial seeds came from a smooth quantum field or from a more radical, discrete, foamy structure as suggested by theories like loop quantum gravity or quantum graphity. The universe's baby picture might just contain hidden within it a photograph of its own quantum gravitational origin. The ultimate frontier may lie in harnessing the strange phenomenon of quantum entanglement itself as a tool for discovery. Theoretical work suggests that the way entanglement entropy behaves in a gravitational field is deeply connected to the geometry of spacetime. By creating complex quantum systems in the lab and studying how their entanglement evolves, we might be able to simulate the conditions of quantum gravity. These analog experiments could allow us to test ideas about the holographic principle and the emergence of spacetime in a controlled setting. It's a bold approach. If we cannot probe the quantum foam of the universe directly, we might instead build a small, simulated version of it in a quantum computer and watch it evolve, learning the rules of quantum gravity from the bottom up. This convergence of quantum information science and gravitation theory is one of the most exciting areas of modern physics, suggesting that the tools to finally understand the fabric of reality may not just be giant telescopes and colliders, but also the intricate, entangled quantum states we are only just learning to engineer. The path to understanding the quantum foam is therefore a multifaceted journey, a grand synthesis of the impossibly large, the infinitesimally small, and the profoundly complex, guiding us toward a future where the universe's most fundamental secret may finally be revealed. And so, we find ourselves at the end of this extraordinary expedition, having navigated a labyrinth of 30 mind-expanding theories. We began by peering into John Wheeler's stormy vision of a spacetime churning with microscopic wormholes and virtual black holes. We then watched as that chaos was reinterpreted, first as the natural turbulence of a cosmic superfluid, and then as the dynamic spin foam of a universe built from indivisible atoms of space. We confronted the staggering possibility that our reality is a holographic projection, a magnificent illusion born from information encoded on a distant boundary. We even dared to consider that time itself might be an emergent illusion, a consequence of increasing quantum entanglement, and that every black hole could be a cosmic womb giving birth to a new universe. We've seen the vacuum's energy threaten to tear the cosmos apart, witnessed the potential for cosmic computers and consciousness itself to be woven from the foam, and grappled with paradoxes that pit the laws of physics against each other at the precipice of a black hole. This wild journey underscores one unifying, profound truth: the quantum foam is more than just a concept. It is the final frontier of human understanding, the ultimate no man's land where the two most successful and yet incompatible theories of all physics, the cosmic gravity of Einstein and the probabilistic weirdness of quantum mechanics, clash in a battle for the soul of reality. It is the mysterious substrate from which everything, from the largest galaxy to the faintest thought, ultimately emerges. The quest to comprehend it is the single greatest scientific challenge of our time, a puzzle that has consumed the finest minds for a century and will likely define the course of physics for the next. What makes this pursuit so electrifying is that the answer is not yet written. We are living through the chapter of human history where the deepest secrets of existence are being actively debated, where every new observation from a gamma ray burst or a gravitational wave detector, every new calculation in a supercomputer, brings us one step closer to a revelation. The universe, as we are discovering, is infinitely stranger, more complex, and more beautifully bizarre than we ever could have imagined from the comfortable confines of our classical world. It is a realm where nothing is fundamental, where everything is relational, and where the very act of observation might play a role in crystallizing reality from a sea of pure potential. This is not the end of the story, but a brilliant and thrilling beginning. The greatest discoveries in science have always come from those who dared to question the seemingly unshakable foundations of their reality, who looked at the smooth, continuous stage of the world and asked, what if it's not smooth at all? That spirit of radical curiosity is what drives us forward, so we turn this final reflection over to you. Which of these 30 theories resonated most deeply with your own sense of wonder? Did the holographic principle reshape your perception of what is real? Does the idea of a universe built from cosmic Lego bricks in causal dynamical triangulation spark your imagination? Or are you captivated by the possibility that every black hole contains a rebounding Planck star, a gateway to a new cosmos? Share your favorite mind-bending concept in the comments below. We are having one of the most profound conversations possible, and your perspective is a vital part of it. If you want to continue this journey of exploration into the heart of cosmic mysteries, make sure to subscribe. There are endless wonders left to uncover, from the nature of dark matter and dark energy to the possibility of other dimensions and the ultimate fate of our universe. The adventure is just beginning. Never stop questioning, because the fabric of reality itself is waiting